To live forever, you must first survive the act of tearing yourself apart. Deep on the dark, unforgiving floor of the Atlantic, there is a creature that possesses what many would consider the holy grail of biology, the potential for infinite youth. But the ocean does not deal in miracles. It deals in ruthless, calculated economics. For this animal, biological immortality is not a gift. It is a terrifying, inescapable cycle of extreme vulnerability. To grow, to heal, to survive the passage of decades, a lobster must repeatedly shed its entire body and walk away from itself. Imagine a life where your greatest protection is also your ultimate prison. The lobster navigates a benthic underworld, a mosaic of jagged rock outcrops, shifting sand patches, suffocating kelp forests, and pitch-black crevices. In this environment, longevity is not guaranteed by blistering speed or overwhelming dominance. It is negotiated through brutal cycles of growth and exposure. The lobster is an armored opportunist. It stalks the seabed with sensory antennae constantly sweeping the darkness, tasting the chemical traces of the water, hunting for mollusks, carrion, and sometimes smaller, weaker crustaceans. It is a walking fortress. Its weapons are asymmetrical and devastating. One massive, blunt claw engineered for crushing shells with immense pounds of pressure, and another sharper, serrated claw built for precision cutting and slicing. Encasing this machinery is a rigid exoskeleton. This shell is a masterpiece of natural engineering, composed of tightly woven chitin and heavily reinforced with calcium carbonate drawn directly from the surrounding sea. It is a shield against the abrasive grit of the ocean floor and the crushing jaws of predators. But unlike the internal skeletons of vertebrates, which grow seamlessly alongside the flesh, this armor is static. It does not stretch. It does not yield. As the lobster feeds and its internal tissues expand, the space inside the shell begins to run out. The armor becomes a claustrophobic trap. Because the skeleton is external, growth cannot occur in gradual, comfortable increments. The only way forward, the only way to accommodate the expanding life inside, is to completely discard the old self and build a new one. This process, known as molting, is a biological spectacle of horror and endurance. It begins long before the visible fracture. Weeks in advance, a silent, internal dismantling takes place. Beneath the hard, scarred exterior of the old exoskeleton, a brand new, incredibly soft shell begins to form. The lobster's body actively starts to reabsorb calcium from its current armor, leaching the minerals out of its own shell and storing them internally in specialized temporary deposits called gastroliths. The animal is literally dissolving its own walls to save the raw materials. During this preparatory phase, the lobster reduces its feeding. It becomes quiet. It retreats into the darkest, most secure crevice it can find. Hormonal signals flood its system, aligning the timing of the molt with seasonal temperature shifts and internal energy reserves. It waits for the precise moment of maximum tension. Then comes a rupture. The lobster rapidly absorbs seawater, intentionally swelling its body mass, forcing the pressure outward into the old, weakened shell cracks. The fracture always occurs along predetermined weak lines, usually splitting horizontally across the back, right where the carapace meets the tail. From this jagged fissure, something pale, soft, and entirely defenseless begins to pull itself free. The extraction is agonizingly slow and demands a staggering expenditure of energy. The lobster must wriggle backward, pulling its delicate new body out of the rigid mold of the old one. Every single appendage must be withdrawn. It must pull its massive, meaty claws through the impossibly narrow joints of its old arms. It must carefully extract its long, fragile antennae, its delicate walking legs, and even the translucent lenses of its eyes. It is an act of sheer, violent exertion. If the lobster is weak, or if a limb becomes lodged within the old shell, the situation instantly becomes lethal. Trapped mid-molt, it will die a slow death inside its own ghost. To prevent this, the lobster possesses a fail-safe, autotomy. If a claw or a leg refuses to slide free, the lobster will voluntarily sever its own limb, leaving it trapped in the old shell to secure the escape of the core body. It will leave a piece of itself behind rather than perish entirely. Once free, the animal leaves behind a perfect, hollow duplicate of itself, an empty, ghostly husk resting on the seafloor. But the victory of extraction is immediately overshadowed by the terror of exposure. The The lobster that emerges is soft, pliable, and entirely stripped of its defenses. For hours, and sometimes days, it is nothing but exposed, gelatinous meat. In the pitch black of the ocean floor, predators are highly attuned to this cycle. The water carries the chemical scent of the molt, a dinner bell for every opportunist in the vicinity. Moray eels, octopuses, large predatory fish, and even other, harder lobsters will not hesitate to exploit a molting individual. The seafloor during molting season transforms into a landscape of silent ambushes. The newly emerged lobster must remain absolutely hidden, paralyzed by vulnerability, pumping water into its soft new tissues to expand them to their new, larger size before the new shell begins to harden. It survives this window through sheer luck and absolute stillness. This is the central, unavoidable paradox of the lobster's existence. To remain biologically young, to repair damage, to grow larger and more formidable, it must periodically submit to total defenselessness. And this brings us to the great myth of the lobster, the idea of immortality. It is true that lobsters do not exhibit predictable patterns of biological aging. Their cells repair with terrifying efficiency. Telomerase, an enzyme specifically linked to cellular maintenance and the prevention of DNA degradation, remains highly active in their tissues throughout their entire lives. While human cells degrade and wither over time, the lobster cells do not lose their edge. In theory, free from disease and predators, a lobster could persist for decades, perhaps pushing a century or more, continuously repairing its own code. But biology is bounded by physics. Lobsters do not die a simple old age, quietly fading away as their organs shut down. They die of exhaustion. They die because the process of molting eventually becomes too mathematically costly. As a lobster ages, it grows larger. As it grows larger, the intervals between molts stretch out. A young, small lobster may molt several times in a single year, rapidly expanding its size. But an ancient massive titan of the seafloor might molt only once every 3, 4, or 5 years. The energy demands scale exponentially with size. Producing a gargantuan exoskeleton requires an astronomical amount of biological material, vast stores of drawn calcium, and a massive reserve of metabolic energy. The physical act of pulling a 40-pound body out of a rigid shell requires muscular force that borders on impossible. The recovery time extends. The vulnerability window widens. Eventually, the animal reaches a threshold. The energy required to execute the molt exceeds the energy the lobster can store. When that day comes, the lobster may fail mid-extraction, dying trapped within the halfway point of its own rebirth. Or, sensing its own depleted reserves, it may simply cease molting altogether. When it stops molting, the shell begins to degrade. It becomes scarred, pitted, and infected by shell disease. Parasites bore into the chitin. The armor that once protected it slowly rots from the outside in until the animal succumbs to the environment. The growth that extended its life ultimately becomes a crushing weight that ends it. But until that final, fatal threshold is reached, a large lobster lives a life of heavy dominance. The burden of mass dictates behavior. Huge lobsters are intensely visible. They require massive amount of oxygen, substantial daily caloric intake, and prime, cavernous shelter spaces to hide their bulk. In densely populated benthic regions, competition for these resources is brutal. Dominant individuals claim the deepest, most secure rock crevices and aggressively defend them against all intruders. Complex social hierarchies emerge in the dark. These hierarchies are navigated through a bizarre combination of chemical warfare and ritualized combat. When two lobsters meet, they do not immediately resort to violence. They engage in antennal fencing, whipping their long sensory organs at one another. At the same time, they utilize a highly specialized method of chemical communication. Lobsters release urine from nozzles located on their faces, right below their eyes. This urine is heavily laced with complex pheromones that broadcast the animal's size, aggressive intent, status, and reproductive readiness directly into the face of its rival. They literally blind each other with chemical resumes of their fighting history. Through these invisible clouds of data, subordinate lobsters will often yield to larger dominance without engaging in full combat, conserving vital energy and avoiding the devastating risk of a crushed limb. But as a lobster continues to grow, It cannot afford to be subordinate. It must continually reassert its dominance, constantly challenging rivals to maintain the premium territory necessary to fuel its massive body. Reproduction introduces an entirely different, equally taxing layer of biological strain. Female lobsters endure a staggering burden to ensure the survival of their bloodline. Once mating occurs, a delicate process that can only happen during the female's vulnerable soft-shell phase immediately after she molts. She carries the fertilized eggs beneath her tail. She does not leave them in a nest. She becomes a nest. For 9 to 11 exhausting months, she carries tens of thousands of tiny, dark eggs glued to her swimmerets. She must constantly fan her tail to oxygenate the brood and clean away fungal infections. During this nearly year-long brooding period, her mobility is reduced, her feeding is limited, her vulnerability skyrockets. When the eggs finally hatch, the larvae are released into the water column. They do not look like lobsters. They are tiny, transparent, alien-like creatures that drift in the open pelagic zone. The mortality rate is apocalyptic. Out of tens of thousands of larvae, perhaps only 1 or 2 will survive the gauntlet of filter feeders, fish, and currents to settle back down to the seafloor and begin the armored phase of their lives. The extreme longevity of the adult is the only mathematical counterweight to the near total annihilation of its youth. Yet, for those that do survive, the lobster's biology offers one more astonishing trick of resilience: regeneration. The benthic floor is a violent place. Limbs are lost constantly to predators, to rock slides, to territorial brawls. But lost claw is not a permanent handicap. It is merely a temporary setback. If a lobster survives the loss of a limb, it will begin to regrow it from the inside out. Over the course of the next several molts, a small, pale bud will appear where the limb was severed. With each subsequent shed, the bud expands, taking shape until fully functional, albeit slightly smaller, claw is restored. In some cases, if the injury occurs early enough in life, the regenerated claw can eventually surpass the original in size. This regenerated capacity grants a lobster an almost supernatural ability to walk away from catastrophic trauma. But like everything else, this magic trick has a price. Pumping resources into regenerating a crushed claw drains energy away from overall body growth. A lobster regrowing a limb will not increase its overall mass as significantly during its next molt. The energy budget is strict. You can repair or you can expand, but doing both pushes the animal dangerously close to its metabolic limits. And today, those limits are being pushed harder than ever by forces far beyond the ocean floor. The Atlantic is changing. Rising ocean temperatures act like an accelerator on the cold-blooded lobster's metabolism, forcing it to burn through energy reserves faster, increasing its demand for food, and potentially misaligning its molting cycles. Furthermore, the oceans are absorbing massive amounts of carbon dioxide, leading to acidification. As the water becomes more acidic, it directly interferes with a lobster's ability to pull calcium carbonate from the sea. The very building blocks required to forge its armor are becoming scarce. A weaker shell means a higher risk of puncture. A more difficult calcification process means a longer, more exhausting recovery post-molt. Add to this the relentless pressure of human harvesting. For centuries, traps have plummeted into the darkness, explicitly targeting the largest, oldest, most resilient individuals. By systematically removing the elders, the titans who have successfully negotiated dozens of molting cycles and hold the deepest genetic memory of survival, humanity has radically altered the population structure of the seafloor. We are leaving behind an ocean skewed towards smaller, younger lobsters, stripping away the very specimens that define the extreme limits of the species' endurance. Yet, despite the warming waters, the acidic currents, and the vanishing elders, the cycle continues in the deep. Beneath a heavy, shadowed rock ledge, a massive, ancient lobster rests in the silt. Its shell is a roadmap of violence, deeply scarred, encrusted with barnacles, faded and thick. It has survived an unimaginable number of shedding cycles. It has spent years of its life as soft, defenseless meat hiding in the dark, and decades as an armored dreadnought wandering the sand. Its long antennae sway gently, tasting the faint chemical trails of the tide. Every slow, measured breath draws icy water across the hidden gills beneath its carapace. It is wearing the shell that keeps it alive, but it knows on an instinctual, cellular level that the shell is shrinking. The pressure is building again. The gastroliths are forming. The internal clock is ticking toward the next rupture. Aging for this creature is not a slow decline into fragility. It is a terrifying, high-stakes negotiation with physics and energy. It is an endurance test measured not in years, but in the repeated willingness to strip away its only defense and face the abyss unprotected. The lobster will continue forward in the silent dark, carrying the heavy, inescapable weight of its next rebirth. It will grow larger, it will grow harder, and it will grow ever more exhausted. The true limit of its existence is not time. It is the agonizing, inescapable cost of breaking out of prison that keeps it alive. The jaws of a predator snap shut with the force of an industrial vice, crushing down on the armored limb of a crab. For almost any other creature on Earth, this moment dictates the end. It is the inescapable anchor of death. When bone is caught, the body must follow. But in the violent, unforgiving arena of the rocky shoreline, the crab refuses to play by the standard rules of biology. There is no desperate thrashing, no paralyzing panic, and no futile tug-of-war against a stronger opponent. Instead, there is a cold, instantaneous calculation. Muscle fibers at the base of the trapped limb violently contract. Connective tissue splits along a perfectly engineered, predetermined seam, and the crab simply tears off its own arm, leaving the severed claw twitching the jaws of the bewildered predator, while the rest of the body rockets backward into the pitch-black safety of a rock crevice. What appears to the untrained eye as a catastrophic, life-ending injury is, in reality, a masterpiece of evolutionary engineering. It is a calculated, flawlessly executed escape. To understand the crab, you must first understand the fundamental philosophy of its existence. Physical integrity is an illusion. To endure a world entirely designed to crush you, you must be willing to sacrifice the parts of yourself you can afford to lose. The habitat of the crab is a realm of perpetual, chaotic collision. Whether clinging to the jagged precipices of a wave-battered intertidal zone, navigating the suffocating roots of a mangrove swamp, or crawling across the exposed flats of a coral reef, the crab exists under permanent siege. Octopus arms, lined with hundreds of tasting, gripping suckers, probe endlessly into the dark spaces where crabs seek refuge. Triggerfish, armed with teeth evolved specifically to shatter calcium carbonate, patrol the waters above. Moray eels bite blindly and savagely into narrow cracks, and seabirds strike in the air with beaks like honed daggers. But the violence does not only come from above or below, it comes from within. Crabs are fiercely territorial, engaging in brutal, gladiatorial combat with their own kind. They lock their massive claws in crushing contests over mates, over shelter, over simple dominance. In this world, severe physical damage is not a rare tragedy. It is the absolute baseline of daily life. To survive this relentless gauntlet, the crab is encased in a rigid exoskeleton, a suit of biological armor forged from chitin and heavily reinforced with crystallized calcium salts drawn from the sea. It is a formidable defense, encasing the soft, vulnerable internal organs like a medieval shield. Spines, serrations, and thickened ridges add structural complexity, designed to shatter the teeth of attackers or prevent a predator from securing a fatal grip. But armor has a fatal flaw. Once a predator breaches a perimeter, once an octopus wraps its arm around a heavy claw, or a fish clamps down on a walking leg, that impenetrable armor instantly transforms into an inescapable liability. If the predator is larger, and it usually is, it will simply use the captured limb as a handle to drag the crab out of its sanctuary and consume it entirely. This is where the crab's ultimate survival mechanism is activated. Deep within the anatomy of the animal, located at the base of every single leg and claw, lies a highly specialized plane of weakness known as the autotomy joint. This is not a flaw in the armor. It is a meticulously designed fracture point, a biological self-destruct sequence. When the crab's nervous system detects a specific threshold of external force, or when it is triggered by voluntary muscular command in a moment of sheer desperation, the joint shatters. The limb detaches with surgical precision. The brilliance of autotomy lies not just in separation, but in the immediate aftermath. The moment the fracture occurs, specialized sphincter muscles at the stump instantaneously clamp shut, violently sealing the blood vessels to prevent a catastrophic hemorrhage. A delicate membrane immediately forms over the wound, locking out the lethal, bacteria-rich seawater. Meanwhile, the discarded limb, now separated from the central nervous system, continues to violently open and close, thrashing wildly. This post-mortem animation is driven by residual neural activity firing blindly within the severed nerves. It is a macabre mechanical decoy. For the 3 or 4 seconds the predator spends fighting a ghost limb, the crab vanishes sideways into the shadows, preserved by the sacrifice of its own flesh. But in nature, survival always carries an invoice. Escaping the jaws of death by amputating a limb buys the crab its life, but it plunges the animal into a brutal state of physical deficit. A crab missing a large, dominant claw, the chela, is immediately handicapped. Its ability to crush the shells of snails or tear apart carrion is severely compromised, sharply reducing its caloric intake just when it needs energy the most. If it loses a walking leg, its meticulously calibrated balance is destroyed. The signature, lightning-fast sideways gait, a movement optimized for sliding rapidly into the narrowest of crevices, becomes a labored, dragging limp. It cannot flee as quickly. It cannot hunt as effectively. More devastatingly, the loss of physical wholeness instantly plummets the crab down the brutal social hierarchy of the reef. In species where males rely on massively enlarged claws for ritualized display and territorial combat, a male who has sacrificed his primary weapon is instantly marginalized. He cannot defend his prime burrow. He cannot intimidate rivals. He is bypassed by females seeking the genetic fitness, signaled by perfectly symmetrical, massive armor. To the rest of the colony, a wounded crab is a weak crab, and weakness is an invitation for further violence. In this battered state, the crab must hide. It must scavenge. It must bide its time. Because the crab does not simply accept its brokenness. It rebuilds. The true marvel of the crab lies not in its ability to tear itself apart, but in its profound capacity for regeneration. The moment the limb is detached, the healing process begins, driven by an invisible cellular fury. Just beneath the sealed stump, a mass of undifferentiated cells begins to gather. These cells, capable of re-entering the earliest developmental pathways of life, begin to rapidly divide and organize. Slowly, microscopically at first, a new structure begins to push outward. This process is entirely synchronized with the crab's molting cycle. Because the crab is locked inside a rigid shell, the new limb cannot simply grow outward into the water. Instead, it must grow entirely within the confines of a soft, folded cuticle pocket hidden just beneath the stump. As the days and weeks pass, this hidden limb bud expands, twisting and folding it on itself like a compressed accordion, waiting for the signal for release. This rebuilding phase requires a staggering toll on the animal's metabolic reserves. Regeneration is not free. The crab must mobilize massive amounts of calcium to forge the new shell segments. Protein synthesis kicks into hyperdrive to build new muscle fibers, nerves, and connective tissue. Every calorie the injured crab manages to scavenge with its remaining limbs is diverted away from overall body growth and channeled directly into furious reconstruction of the missing piece. If the crab is starving, or if the environment is depleted of resources, the hormonal signals delay the molt and the crab remains broken. But if it finds enough fuel, the endocrine system, flooded with ecdystroids, triggers a molt. The crab retreats into the darkest, tightest fissure it can find. The old, battered exoskeleton splits open, and the animal slowly, agonizingly pulls its soft body free. It is in this terrifying window of total defenselessness that the magic occurs. As the crab extracts itself, the tightly folded limb bud is finally released from its internal pocket. Hydrostatic pressure from the animal's bodily fluids rushes into the new appendage, violently inflating it like a long balloon. When the new shell finally hardens hours later, the crab stands whole once more. The regenerated claw is often noticeably smaller than the original, paler in color, and lacking the heavy scarring of an experienced weapon. But it is functional. It can grip, it can walk, it can defend. With each successive molting cycle over the coming years, the regenerated limb will continue to increase in size, eventually catching up to proportions of the rest of the body. In some fascinating cases, a crab that loses its massively dominant crusher claw will regenerate a smaller, faster cutter claw in its place, while the original, smaller cutter claw slowly morphs into the massive crusher over several molts, completely flipping the animal's physical asymmetry. The body adapts. It reconfigures its weaponry based on what was lost and what remains. This extreme biological elasticity allows the crab to survive a lifetime of continuous traumatic injury. Walk along any densely populated tidal pool or reef edge and look closely at the crab populations. You will rarely find an old crab that is perfectly intact. You will see asymmetrical claws. You will see legs that are a fraction of the size of their counterparts. You will see deep gouges and heel fractures etched into their carapace. To the human eye, they look like the walking wounded. But these marks are not symbols of fragility. They are the battle commendations of the benthic floor. They are living proof of an organism that has repeatedly stared down death, paid the toll in flesh, and walked away. However, this system of sacrifice and regeneration is not infinite. There is a cold, mathematical limit to what the crab can endure. If a crab is subjected to an environment where the rate of injury outpaces the speed of the molting cycle, the animal enters a death spiral. If an octopus tears off 3 legs and a territorial rival crushes a claw before the crab can initiate a molt, locomotion becomes nearly impossible. It cannot forage enough calories to fuel the massive metabolic demands of regenerating 4 limbs simultaneously. It starves, or it is simply caught again, this time with nothing left to sacrifice. Predators, driven by the same ruthless evolutionary forces, have learned to exploit this. Certain fish and octopuses do not aim for a clean kill on their first strike. They will intentionally target the legs of a crab, methodically dismembering it, knowing that a crab missing multiple limbs is slower, uncoordinated, and infinitely easier to drag from its burrow. In some coastal ecosystems, human harvesting relies on this very biology. Fisheries capture crabs, forcefully tear off their massive meat-filled claws, and throw the living, amputated animals back into the ocean, assuming the regenerative cycle will act as a limitless resource. But repeated massive trauma, combined with the stress of capture and the fierce competition of the seabed, often pushes a crab past its physiological breaking point. The energy debt becomes too massive to repay. The system collapses. The crab dies. The survival of the crab hinges on a delicate, terrifying balance. It operates on the principle that the periphery is entirely expendable, provided the core remains intact. It is a life spent navigating the jagged edge between enough damage to escape and too much damage to survive. As the tide recedes on a twilight shoreline, exposing the slick, algae-covered rocks to the cooling air, the inhabitants of the intertidal zone emerge from their aquatic bunkers. A crab steps out from beneath a heavy stone overhang. Its posture is slightly uneven. It steps carefully, redistributing its weight to compensate for a missing right walking leg. The stump is clean, perfectly sealed, already pulsing with the microscopic beginnings of new life beneath the shell. Its left claw is massive, heavily armored, and scarred from previous wars. Its right claw is smooth, pale, and only half the size, the result of a sacrifice made 2 molts prior. It moves sideways into the fading light, its stalked eyes scanning the horizon for shadows, its antennae tasting the salt spray for the scent of carrion or competition. It is not a perfect specimen. It is not whole, but in the violent, crashing reality of the ocean's edge, wholeness is a luxury that gets you killed. Perfection is rigid and rigidity shatters. The crab survives because it understands the ultimate truth of its environment. Endurance is not about being impenetrable. It is about being recoverable. It is about the absolute, unflinching willingness to leave pieces of yourself behind in the jaws of the dark, trusting that the core of who you are is strong enough to rebuild from the wreckage. And so, scarred, asymmetrical, and missing pieces of its own architecture, the crab presses forward into the night, ready, if necessary, to break itself all over again. A silver torpedo tears through the open ocean at highway speed, and it does not slow down. Minutes bleed into hours, hours dissolve into days, and still, the fish does not glide to a resting halt. It does not sink into the quiet stillness of the deep to sleep. It keeps moving. Its muscles burn, its massive heart hammers against its ribs, and the water continuously splits around a body that has been engineered for absolute, relentless motion. In a marine world where the vast majority of fish drift, hover, and rely on short, panic bursts of speed to survive, the tuna lives in a state of permanent acceleration. For this animal, the greatest danger in the ocean is not a larger predator. The greatest danger is stopping. Far beyond the intricate, bustling architecture of coral reefs and miles away from the sheltering contours of the coastline lies the pelagic zone. The open ocean is a blue desert, defined by its terrifying immensity and brutal scarcity. There are no walls to hide behind. There are no jagged rocks to wedge into when trouble arrives. The landscape consists only of shifting, ephemeral clouds of prey, predators that patrol territories the size of small countries, and invisible currents carving highways through a water column that plunges downward into crushing, pitch-black emptiness. In this boundless void, survival does not favor the heavily armored or the perfectly camouflaged. Survival here heavily favors the efficient. It favors those who can devour enormous distances without collapsing. The tuna has answered the brutal demands of this blue desert by developing one of the most extreme, highly tuned endurance systems in the history of biology. Its body is a masterclass in fluid dynamics. From the sharp, pointed tip of its snout to the rigid, crescent-shaped sweep of its tail, every single contour is designed to eradicate drag. When the tuna accelerates, its fins do not just lay flat. They fold precisely into custom-shaped grooves recessed along the sides of the body, perfectly sealing the hull to minimize microscopic turbulence. The tail itself is not a flexible paddle, but a stiff, side-like blade. It oscillates with rapid, incredibly tight motion, transferring every ounce of muscular energy directly into forward thrust with zero wasted effort. It is a biological missile. But flawless hydrodynamics alone cannot explain how a tuna maintains a cruising velocity that would completely exhaust almost any other fish in a matter of seconds. The true, terrifying secret of the tuna's endurance lies hidden deep within its flesh. It lies in heat. Unlike the vast majority of bony fish on the planet, which are entirely cold-blooded and at the total mercy of the surrounding water temperature, the tuna is a regional endotherm. It possesses a near-mythical ability to elevate the temperature of its swimming muscles significantly above the freezing currents it swims through. This is not full mammalian warm-bloodedness, but it is a radical, evolutionary deviation from standard fish design. In the brutal physics of biology, warm muscle contracts faster and with exponentially more power than cold muscle. The complex enzymatic reactions that drive cellular metabolism fire with staggering efficiency at higher temperatures. In deep, frigid waters where other predators grow stiff, sluggish, and unresponsive, the tuna maintains explosive performance of a warm-blooded killer. This internal furnace is fueled by the continuous, rhythmic firing of the tuna's muscles and is locked inside the body by a miraculous piece of anatomical plumbing known as the rete mirabile, the wonderful net. Deep inside the fish, the blood vessels carrying naturally warm blood away from the actively working swimming muscles are woven tightly alongside the vessels, carrying freezing, oxygen-rich blood returning from the gills. As the fluids pass each other, the warm blood transfers its heat directly to the cold blood. It is a flawless countercurrent heat exchange system. Instead of radiating its precious metabolic warmth out into the icy ocean, the tuna traps it, creating a tightly sealed thermal pocket deep within its core. The effect of this trapped heat is utterly transformative. Elevated muscle temperatures drastically enhance the fish's aerobic capacity. If you were to look inside a tuna, you would see that its body composition is dominated by dark, blood-rich red muscle fibers. Unlike the pale white muscle fibers used by reef fish for frantic, 3-second sprints, these red fibers are packed dense with mitochondria and myoglobin. They are highly specialized engines designed strictly for oxygen-dependent metabolism and sustained, unending contraction. But running a warm, high-performance aerobic engine demands astronomical quantities of fuel and oxygen. To feed this system, the tuna's internal machinery is scaled to monstrous proportions. Its heart is massive relative to its body size, pumping thick, heavily oxygenated blood at immense pressures to ensure the deep tissues never starve. Its gills are beautifully expansive, possessing a massive surface area of delicate filaments designed to strip every possible molecule of oxygen from the passing seawater. Because the tuna operates almost entirely on this aerobic system, it avoids the rapid buildup of lactic acid that paralyzes other fish after sprint. It can cruise swiftly for days on end without accumulating an ounce of metabolic debt. Yet, this magnificent system comes with a terrifying, non-negotiable catch. To force enough water over those massive gills to feed that massive heart, the water must be constantly moving. Tuna are obligate ram ventilators. They have entirely lost the ability to pump water over their gills while remaining stationary. If a tuna stops swimming, the flow of oxygen instantly drops to zero. It will suffocate in the open ocean. Movement is not an option. It is not a hunting strategy. It is mandatory life support. In this profound sense, the tuna is both the undisputed master of speed and its absolute prisoner across the pelagic expanse. Tuna rarely travel alone. They move in massive schools, coordinated squadrons of silver missiles acting with single-minded purpose. Grouping provides a vital hydrodynamic draft. Fish positioned in the center of the formation experience slightly reduced drag, allowing them to conserve precious energy in the slipstream of the vanguard. Simultaneously, this collective, glittering movement visually confuses predators and orchestrates the destruction of their prey. Each individual must perfectly maintain its position relative to its neighbors, matching velocity and trajectory to the millimeter to avoid catastrophic, high-speed collisions. When the school locates prey, often smaller, highly agile fish or squid, the tuna escalate from cruising speed to an explosive, weaponized sprint. They operate like sheepdogs of the abyss, aggressively herding their targets upward, compressing them against the ceiling of the ocean's surface into tight, swirling bait balls. In these violent feeding frenzies, the tuna's speed reaches its terrifying zenith. The school corrals a target, systematically eliminating every avenue of escape, while seabirds plummet from the sky and dolphins tear into fray from the flanks. But this hunt exposes the razor-thin margin of the tuna's existence. They are built for infinite endurance, yet they are fully capable of unleashing bursts of speed that push right up against their absolute physiological ceiling. The exact same warm, red muscle that allows them to cruise effortlessly also grants them the power to accelerate like a fired bullet. But pushing that close to maximum output causes their energy expenditure to spike exponentially. The drag of the water increases with the square of their speed. Doubling their velocity demands infinitely more than double the energy. The margin between a sustainable sprint and total cardiovascular exhaustion is terrifyingly narrow. If a tuna miscalculates its pacing, it risks burning out, and they cannot afford to burn out because their migrations are the stuff of legend. Some species of tuna traverse entire ocean basins, tracing invisible temperature gradients and prey availability across thousands of miles of featureless blue. Their endothermic muscles allow them to dive into freezing, highly productive feeding grounds where their cold-blooded competitors simply cannot function. It expands their empire across the globe. But heat, speed, and distance must all be paid from the brutal currency of calories. Maintaining an elevated core temperature requires a relentless, voracious intake of fuel. A tuna is always hungry. If the delicate balance of the ocean shifts, if a current moves, or a prey population collapses, the consequences are immediate and severe. Without massive daily caloric intake, the endurance engine begins to sputter. Growth stops. Reproductive output crashes. Reproduction itself is a massive energetic drain. Tuna travel vast distances back to warm, nutrient-poor waters simply to spawn, releasing millions of eggs into the currents where larval mortality is absolute carnage. The adults must somehow balance the catastrophic energy drain of migration, the high-speed pursuit of prey, and the biological mandate to reproduce, all while chained to the treadmill of continuous forward motion. They also must navigate the shifting, three-dimensional maze of the water column itself. The ocean is deeply stratified. In the cold, crushing depths, metabolic rates are challenged. Hypoxic zones, massive layers of water completely devoid of oxygen, force the tuna to constantly adjust their cruising depth, seeking the perfect, razor-thin equilibrium between the temperature they need to keep their muscles warm and the oxygen they need to keep their massive hearts beating. They outrun sharks and billfish not by outmaneuvering them, but by holding a top speed for longer than pursuers' physiology can withstand. For the tuna, endurance is literal armor, but this perfect evolutionary design has meta-force it cannot outswim. The very traits that make the tuna the apex endurance hunter of the open ocean. Their predictable, massive migratory routes, their dense schooling behavior, and their need to remain in highly oxygenated surface waters make them uniquely vulnerable to industrial human fishing. Massive purse seine nets and endless miles of long lines intercept these moving cities of fish. By extracting the largest, most mature individuals, we are systematically dismantling the population dynamics of the greatest biological engine the sea has ever produced. Yet, far beyond the reach of the floating factories, out in the vast, unbroken wilderness of the pelagic zone, the design holds true. As twilight bleeds across the horizon and the water deepens into bruised purple, a school of tuna glides just beneath the rippling surface. Their bodies flash silver and cobalt in the dying light. They do not pause as the night takes over. They do not rest. Their tails sweep in a perfect, synchronized rhythm, an unbroken mechanical heartbeat propelling them into the dark. Beneath them lies the crushing abyss. Above them, a sky mirroring the emptiness of the sea. The ocean offers them absolutely no sanctuary for stillness. To survive in this world is to move. It is to endlessly convert oxygen and flesh into raw, unyielding momentum. And the tuna has embraced this unforgiving demand completely, living an entire life on a violent boundary where energy supply meets energy demand, a warm heart beating furiously in a freezing sea, proving to the void that endurance, pure, unbroken forward motion, is the ultimate form of dominance. A serpent vanishes beneath the shattered mirror of the ocean's surface and does not come back for air. Minutes bleed away, then more minutes. In a dense, heavy medium that holds absolutely no breathable oxygen for a reptile, its long, patterned body remains submerged, weaving effortlessly through the dark, jagged labyrinths of coral corridors, as if suffocation were nothing more than a terrestrial myth. Any land snake, forced below the surface for even a fraction of this time, would panic, flood its lungs, and drown. Yet this creature continues to hunt. Its heart beats slower with every passing second. Its lungs are held tight and full, and its skin is quietly, invisibly stealing life from the sea itself. The reef around it pulses with a frantic, restless movement of 1,000 other lives. Shafts of filtered, prismatic light cut down to the heavy blue water, illuminating branching coral networks and pitch-black overhangs where fish cluster tightly in nervous, shimmering schools. Through this chaotic metropolis, the sea snake moves without a single ounce of hurry. It is a creature redesigned by the ocean. Its body is laterally compressed, flattened from side to side like a living ribbon, terminating in a tail shaped exactly like a paddle. Every undulation of its spine is a masterpiece of precise, economical physics. It is not built for the explosive, exhausting sprinting of the barracuda. It is built for the slow, agonizing burn of endurance. Each measured flick of muscle, each subtle turn of its head, burns a fraction of its most precious, irreplaceable currency, oxygen. And oxygen is the one resource this silent hunter cannot replenish at will. To survive in a world that constantly demands breath, the sea snake has completely overhauled its internal architecture. Inside its chest, the standard reptilian blueprint has been stretched to the absolute extreme. A single, massively elongated lung runs nearly the entire length of its slender body. This organ is a biological marvel, functioning not only as a massive respiratory reservoir, but as a highly calibrated buoyancy regulator. Before initiating a dive, the snake surfaces for a fraction of a second, taking one deliberate, gasping breath. That elongated lung inflates like a slender internal balloon, packing in a reserve of air that must mathematically sustain the animal until its next ascent. But holding a breath is only the first, most primitive part of the strategy. Once the snake slips below the waves, something far subtler, far more complex begins to happen. The heavy salt water presses against its scales, flowing across a patterned exterior that appears thick and impermeable at first glance. Yet, hidden just beneath that tough, armored skin lies a dense, intricate network of microscopic capillaries pushed unusually close to the surface. In certain species of sea snake, particularly those pelagic wanderers that spend the vast majority of their lives entirely offshore, the skin itself actively participates in respiration. Through a miracle of biological diffusion, dissolved oxygen suspended in the seawater passes directly across the skin and into the snake's bloodstream, actively supplementing the diminishing air stored inside the lung. It is not enough oxygen to replace a breath entirely. The physics are too unforgiving, and the concentration of oxygen in seawater is drastically lower than the atmosphere, but it is enough to extend a lethal dive by a critical, life-saving margin. In dead, still water, this cutaneous breathing is a modest trickle. But when the snake swims into moving currents, or when the ocean surge actively refreshes the boundary layer of water rushing over its body, the intake of oxygen becomes profoundly significant. Yet, even with skin that breathes, the math of survival under pressure is brutally strict. The only way to truly stretch a finite supply of air is to burn it as slowly as physically possible. And here lies the sea snake's second, far more dramatic adaptation: the deliberate, extreme throttling of life's internal pace. The moment the snake's head slips beneath the surface, a reflex triggers a massive metabolic suppression. The animal's heart rate drops off a cliff. Blood flow is immediately and strategically shunted away from the periphery. The circulatory system prioritizes the brain and the most essential internal organs, ruthlessly restricting blood to the outer muscles and tissues, forcing them to tolerate temporary, agonizing hypoxia. All unnecessary muscular activity ceases. Even the deeply energy-intensive process of digestion grinds to a halt if a meal has recently been consumed. The entire body powers down. It becomes a living machine operating in a profound state of biological low-power mode. This metabolic crash is not an accident. It is evolution's ultimate answer to the constraint of water. A reptile cannot extract a full breath from the ocean using gills. It must bring its atmosphere down into the dark with it. In sterile laboratory studies, certain sea snakes have been forced into controlled dives exceeding 2 agonizing hours without surfacing. Out in the wild, the reality of the hunt usually limits these dives to between 30 minutes and an hour, but during extended, desperate foraging sessions deep within the reef matrix or out in the blue void, the difference between a short, failed dive and a long, successful one is simply the difference between feeding and starvation. And hunger is what ultimately tightens this dangerous biological balance. The reef does not surrender its calories easily. Many sea snakes are highly specialized predators, evolved to hunt small, terrified fish hiding deep within jagged crevices, or heavily muscled moray eels that retreat backward into suffocatingly narrow coral tunnels. To capture this hidden prey, the snake must probe the darkest, most confined spaces of the reef. It must writhe and twist its body into dead-end cavities where turning around becomes physically impossible and where the water flow stagnates. Every single probing movement costs oxygen. Every muscular contraction burns a reserve. Every failed strike, every missed opportunity, violently drains a tank that cannot be refilled underwater. The predator is trapped in a permanent, instinctual calculation. Asterisk, how long can I remain below before the ascent becomes mandatory? How deep can I push this breath before the darkness takes over? Asterisk. Yet, the sea snake's deadly design pushes it continuously toward risk. Its venom is a terrifying chemical weapon, a potent neurotoxin capable of paralyzing prey in a matter of seconds. But this venom was not evolved merely for cruelty or overwhelming dominance. It was evolved for extreme metabolic efficiency. When a sea snake strikes a hidden fish, it does not wrestle. It does not waste precious oxygen on a violently thrashing, prolonged struggle, nor does it attempt to slowly constrict its victim. It delivers one precise, devastating bite, and then it simply waits. The paralysis spreads like ice through the small fish's nervous system, instantly terminating the struggle and completely eliminating the predator's need to burn oxygen subduing it. The sheer, overwhelming toxicity of its venom is not just a weapon of death, it is an oxygen-saving device. But even the most potent venom cannot shorten every hunt. Sometimes, dying prey will wedge its body deep within the rigid matrix of the coral, locking its fins into the stone. The snake is forced to linger. It must insert its head deep into the crushing darkness of the hole, its long body coiled exposed in the open water, pulling and twisting to extract its meal. In these prolonged, desperate moments, the snake's entire physiology hangs by a thread on a fragile, invisible equation. Its lung volume strictly dictates its buoyancy. Too much air held in the lung, and the snake floats helplessly upward, fighting to stay near the bottom. Too little air, and it sinks like a stone, dragging along the abrasive reef. The The muscular effort required simply to maintain its position in the water column spikes its oxygen consumption. A single slight miscalculation in buoyancy, a sudden shift in the current, and the desperate, burning need to surface will force the snake to abandon its hard-won meal at the worst possible instant. The ocean continuously compounds this terrifying challenge. Tides and currents sweep across the reef faces unpredictably. Fast-moving water increases the flow of oxygenated sea across the snake's skin, brilliantly enhancing its cutaneous absorption, yet simultaneously demanding far more muscular effort to avoid being swept away. In calm, stagnant lagoons, the energy cost of holding position drops to near zero, but the oxygen uptake through the skin is smothered by a dead boundary layer of still water. There is no simple, guaranteed advantage in this world. Every single environment, every shift in the tide, forces the snake into a frantic internal recalibration. Then there is the crushing reality of depth. As the sea snake descends down the reef wall, hydrostatic pressure violently compresses the air held within its elongated lung. The organ physically shrinks, severely reducing its volume and completely altering the animal's carefully calculated buoyancy. The snake must compensate with incredibly subtle body adjustments, sometimes even intentionally releasing tiny, precious bubbles of air from his mouth before initiating a deep dive just to achieve perfect neutral buoyancy at its target depth. But this lung compression carries a secondary, hidden danger. As the lung shrinks under pressure, the internal surface area available for gas exchange drastically drops. When the snake finally abandons a hunt and begins its ascent, the sudden drop in pressure causes the lung to rapidly re-expand. This can lead to massive, abrupt spikes and crashes in blood oxygen levels, demanding flawless physiological control to avoid disorientation or blacking out before it breaks the surface. And the deepest, darkest paradox of all emerges when considering the exhaust of life. Carbon dioxide, running out of oxygen, is not the only constraint dragging the snake back to the sky. In all air-breathing animals, it is the accumulation of toxic carbon dioxide in the blood that actually triggers the overwhelming, panicking urge to breathe. Sea snakes exhibit a terrifying, almost alien tolerance for elevated carbon dioxide levels. Their internal chemoreceptors are profoundly desensitized, and their blood buffering systems are immensely robust, allowing them to delay resurfacing far beyond the point where any terrestrial reptile would succumb to toxic shock. They operate as close to the absolute physiological limit of life as an animal can, but this tolerance is not infinite. If the snake pushes a dive just 1 minute too far, muscle coordination begins to falter. Reflexes slow. The body begins to shut down and vulnerability spikes. Because down here, the sea snake is not invincible. It is a predator, but it is also prey. Massive reef sharks, aggressive groupers, and plunging seabirds actively hunt them. Surfacing frequently exposes the snake to the sharp eyes of aerial predators circling above. Staying submerged too long risks a silent, hypoxic death in the dark. The snake's entire behavior is a constant, agonizing compromise between two absolute dangers: suffocation below and violent execution above. It must choose the lesser threat, moment by moment, breath by breath. Reproduction only complicates this terrifying oxygen equation further. Many species of sea snakes have abandoned the land entirely. They are viviparous, giving birth to live, perfectly formed young directly into the open ocean. Pregnant females carry a heavy brood of developing embryos deep within their bodies. This added, growing mass demands a massive increase in the mother's baseline metabolic rate. More living tissue requires far more oxygen. Yet, the desperate need to feed intensifies during this gestation period. A gravid female, heavy with unborn life, is forced to push her dive times closer and closer to her absolute lethal limit just to secure enough prey for 2 generations. She balances her own immediate survival with the demanding, parasitic drain of her offspring. The ocean offers absolutely no maternity leave, no sanctuary, no rest. It offers only constraint. And yet, despite all of these extreme, breathtaking adaptations, the skin that breathes, the heart that stops, the lung that stretches the length of a body, sea snakes remain inescapably air breathers. The ocean is not their true home. It is an environment they are merely hacking. They must always, eventually, return to the sky. When they do, The ascent is often steep, abrupt, and desperate. A sinuous, patterned form rises like a ghost through the heavy blue water, breaking the tension of the surface with nothing more than a tiny, almost invisible ripple. The exhalation and the subsequent inhalation are violent and instantaneous, sometimes lasting only a fraction of a second to completely refill the massive lung. And then, as quickly as it appeared, the head slips back under. It vanishes. The surface visit is brutally brief, furtive, and paranoid, minimizing exposure to the sky to the absolute bare minimum. The larger ecological implication of this endless, terrifying balancing act is profound. By aggressively exploiting these underwater niches for extended periods, by plunging into the suffocating crevices where fish believe they are safe, sea snakes occupy an apex role that almost no other reptile could sustain. They relentlessly regulate the populations of cryptic reef fish and heavily armored eels, completely shaping the hidden microcommunities buried within the coral structure. Their specific predation patterns dictate which species dominate the shadows and how energy flows through the darkest arteries of the reef system. Oxygen limitation does not restrict these animals to the useless margins of the ecosystem. It is the very chisel that sculpts their massive influence. But this balance is unimaginably delicate. Warming oceans are actively stripping dissolved oxygen out of the water, shrinking the critical margin available for the snake's cutaneous skin absorption. Massive, dead hypoxic zones are expanding like tumors in coastal waters, making extended dives infinitely more dangerous. A biological system, perfectly, meticulously tuned to a razor-thin oxygen gradient, is now facing a future of absolute chemical uncertainty. The sea snake's ancient, flawless compromise between lung and skin, between metabolism and motion, is about to confront conditions far outside its evolutionary memory. Deep in the twilight waters, along a vertical, plunging reef wall, the sea snake glides downward. Its body is a seamless ribbon of patterned, oxygen-starved muscle. It pauses near a shadowed, narrow crevice. It senses a flickering, panicked electrical movement of a hidden eel, and it smoothly slips forward into the blackness. The hunt unfolds agonizingly slowly. It is deliberate. It is calculated. The time underwater stretches out. The stored oxygen reserves grow dangerously thin. The carbon dioxide builds in the blood. Yet the snake remains totally composed. Its heart is slowed to crawl. Its metabolism is locked in chains, and its skin is quietly, desperately absorbing whatever microscopic traces of life the sea can spare. When it finally abandons a reef and ascends, breaking the surface for that one swift, gasping breath, the motion appears graceful. It looks effortless. But beneath that smooth, rippling rhythm lies a lifetime of constant, terrifying negotiation. Every single dive is a wager with death. Every hunt is mathematically measured against the invisible, ticking countdown of oxygen in the blood. Survival in this blue void is not about sheer speed or heavy armor or brute force. It is about the absolute mastery of operating exactly at the edge of suffocation without ever crossing the line. In a world defined entirely by water, this reptile lives suspended between two hostile realms, borrowing air from the sky above and stealing oxygen from the abyss below, intentionally slowing its own pulse to forcefully stretch seconds into minutes. The ocean never stops demanding breath, and the sea snake never stops calculating exactly how long it can refuse. The ocean at the bottom of the world is cold enough to kill in a matter of minutes. It is a dense, crushing, lightless void where the temperature hovers perpetually just below the point at which fresh water would completely solidify into ice. It is an environment that actively despises warmth. Yet, standing on the edge of a shattered ice shelf, looking down into the black abyss, something sleek, black, and white prepares to slice through the freezing water as if the lethal cold were entirely harmless. With a sudden, fearless plunge, the penguin drops into the darkness. The sea immediately presses against it with silent, relentless, inescapable force. This water is not just a habitat. It is a thermodynamic vacuum, drawing heat from flesh, blood, and bone with terrifying mathematical precision. Water extracts heat approximately 20 times faster than air at the exact same temperature. In these specific Antarctic waters, exposed human skin would burn with the agony of the cold before sensation vanished entirely. Muscles would seize and stiffen into useless rock. The heart would stutter, misfire, and stop. Blood would slow to a freezing sludge. But the penguin does not shiver. It does not hesitate. It does not go into shock. It hunts. As it descends into the crushing depths, a stream of silver air bubbles trails from its feathers, glittering like diamonds in the faint blue twilight. Each of those bubbles is a tiny fragment of stolen warmth, a microscopic rebellion refusing to surrender to the void. The water is dense, heavy, and totally unforgiving. Every single second spent submerged is a brutal, high-stakes contest between internal biological heat and external planetary cold. The physics of this world are simple, absolute, and merciless. Heat always flows from warm bodies to cold surroundings. In the seas of Antarctica, that gradient is overwhelmingly steep. Yet, deep inside the chest of this compact biological torpedo, the core temperature remains astonishingly, almost impossibly stable. Its heart continues to beat, not in the frantic, fluttering panic of a dying animal, but at a slow, measured, hypnotic rhythm optimized purely for oxygen conservation. Its heavily muscled wings, now transformed by millions of years of evolution into rigid hydrodynamic flippers, flex with devastating power, tearing through the water column. Its eyes dilate, adjusting perfectly to the suffocating blue gloom. The mystery of the penguin is not how it manages to catch fish in this nightmare environment. The true, staggering mystery is how it does not freeze from the inside out. The answer begins with the sheer genius of its architecture. The body of a penguin is not merely a vessel. It is a meticulously engineered fortress built specifically to withstand a permanent thermal siege. Beneath the smooth, painted contour of its outer appearance lies a dense, impenetrable underlayer of specialized down feathers. These feathers do not sit loosely like those of flying birds. They are interlocked so tightly, woven with such microscopic density, that neither the screaming wind nor the crushing water can penetrate the barrier. Each individual feather overlaps the next in a rigid, scale-like arrangement, coated in waterproofing oil secreted from a gland near the tail. Together, they form a continuous, unbroken shield that traps a highly critical, thin layer of insulating air directly against the bird's skin. Air is an exceptionally poor conductor of heat. By locking this air against its body, the penguin essentially wraps itself in a biological vacuum flask. When the bird dives, the immense hydrostatic pressure of the deep ocean physically compresses this air layer, crushing it down. But the engineering is so flawless that it never vanishes entirely. Even hundreds of feet down in the blackest, coldest reaches of the dive, a residual insulating envelope remains intact, drastically reducing the direct, lethal contact between the animal's skin and the freezing seawater. But feathers and air are only the first wall of the fortress. Directly beneath the skin lies another, heavier line of defense, a massive, thick deposit of subcutaneous fat. This dense blubber layer serves a dual purpose. First, it acts as profound physical insulation. Fat conducts heat far more slowly than muscle or blood, creating a massive thermal gradient. The core remains a burning engine of life, while the outer layers remain cold, ensuring that precious heat does not bleed out into the ocean. Second, this blubber is an energy reserve, a biological bank account of sheer survival during the endless, agonizing periods of fasting. When the shifting sea ice traps the colony miles away from the open water, these fat reserves become the only metabolic currency that matters. The exact same blubber that physically insulates the bird against the external cold is actively burned to fuel the internal furnace that keeps the heart beating. Yet, extreme insulation alone cannot explain survival in near-zero seas. Even the most heavily insulated body risks rapid, catastrophic cooling when submerged for hours a day. The true, hidden vulnerability of any warm-blooded animal lies in its extremities. The flippers in the feet cannot be wrapped in thick blubber or dense feathers, or they would become useless for swimming and walking. They are exposed flesh, bone, and blood, plunging directly into the ice. Why doesn't the blood inside them freeze? Why doesn't the cold travel up the veins and stop the heart? The secret lies deep within the penguin's circulatory plumbing. Inside the shoulders, the flippers, and the top of the legs, the arteries and the veins do not travel independently. They are woven together in incredibly tight, complex bundles known as a countercurrent heat exchange system. As warm, highly oxygenated arterial blood leaves the burning core of the bird's body and travels down toward the exposed, freezing foot. It passes directly alongside the veins, carrying cold, oxygen-depleted blood back up from the toes. Because the vessels are pressed so intimately together, the heat jumps the gap. The warm blood traveling outward actively surrenders its heat to the cold blood, returning inward. By the time the arterial blood actually reaches the webbing of the foot, it has already been intentionally cooled, its heat stripped away and sent back to the core. The extremities remain just a fraction of a degree above absolute freezing. Meanwhile, the cold venous blood returning from the ice is pre-warmed before it ever re-enters the body's sensitive center. This is a masterpiece of thermodynamic engineering. The body intentionally allows its peripheral tissues to cool to the absolute brink of freezing, deliberately reducing the temperature difference between the limb and the environment. With less difference, less heat escapes. It is a controlled, calculated biological surrender at the edges, executed perfectly to protect the vital center. The effect is staggering to witness. A penguin can stand perfectly still on a block of solid, glacial ice for days on end, and its feet will not melt the ice beneath them. No heat is wasted. No warmth is given to the earth. But eventually, the penguin must leave the water. It must return to the land, to the vast, blinding, unbroken sheets of Antarctica. And here, the strategy of survival shifts dramatically. When the katabatic winds sweep across the frozen continent, they bring a cold that defies human comprehension. These are gravity-driven winds, accelerating down the slopes of the polar plateau, reaching hurricane speeds, carrying invisible shards of ice that scour the landscape. In these conditions, individual insulation, no matter how perfectly engineered, is mathematically insufficient. A solitary penguin, caught alone in a wide-out blizzard with winds exceeding 100 miles an hour, will lose heat far faster than its internal metabolism can ever hope to replace it. It will freeze solid, and so individual survival is abandoned. The birds gather. Hundreds and sometimes many thousands of penguins press their bodies together in massive, incredibly dense formations known as huddles. From an aerial view, this massive body ceases to look like a flock of birds. It moves, breathes, and shifts like a single massive superorganism. At the absolute perimeter of the huddle, the birds on the outside face the full, screaming, unrelenting brunt of the storm. They act as a living wall, absorbing the killing cold that would otherwise infiltrate and destroy the group. But they do not stand still. Slowly, almost imperceptibly, the entire formation rotates in a hypnotic, fluid rhythm. The individuals on the freezing outer edge take tiny, measured steps, constantly working their way along the flank, and eventually slipping into the warm, protected interior of a mass. In turn, those who have been deeply warmed at the dead center of the huddle are slowly pushed outward to take their shift against the wind. It is not random, frantic chaos. It is dynamic, thermodynamic equilibrium. The body heat generated by thousands of burning metabolisms is trapped within the living architecture of the huddle, raising the ambient internal temperature to a staggering degree, sometimes tens of degrees warmer than the lethal air howling just inches away. This behavior is not born of sentimental cooperation. It is cold, hard thermodynamic necessity. In the center of the huddle, a penguin's metabolic cost plummets. The energy required to stay alive drops drastically. Less fat burned simply to stay warm means more fat conserved for the ultimate, most agonizing test of all, reproduction. Because the cold is not just an external environmental threat. It is the absolute defining constraint on the future of their species. Emperor penguins, the largest of all, choose to breed in the absolute dead of the Antarctic winter. They lay their eggs in conditions that would crystallize embryonic life within seconds. There are no nests. There are no warm burrows. There's only the ice, the wind, and the dark. When the female lays a single, precious egg, she transfers it immediately to the male. This transfer is a moment of terrifying vulnerability. If the egg touches the glacial ice for more than a few seconds, the life inside will be permanently extinguished. The male catches the egg and gently rolls it directly onto the tops of his own feet. He then lowers a specialized, heavily vascularized fold of abdominal skin, the brood patch, completely over the egg. The unborn chick never touches the ground. It rests suspended precariously above a frozen continent, insulated from the abyss solely by its father's flesh. For the next 2 months of perpetual, sunless darkness, The male will not eat. He will stand in the howling blizzards, shuffling within the massive huddles, his feet acting as a cradle, his body acting as a shield. He will slowly, painfully starve, burning through every ounce of stored blubber to keep both himself and his developing young alive. The stability of the fragile life inside that shell depends entirely on the total, agonizing sacrifice occurring outside of it. The entire shape of the animal is a testament to this war against the cold. Their bodies are compact, dense, and perfectly streamlined. This minimizes their surface area to volume ratio. In the physics of survival, a lower surface area means there is less physical space for heat to escape into the void. They have traded the hollow bones and lightweight frames required for aerial flight for heavy, solid bones that grant them neutral buoyancy in the water and physical sturdiness against the crushing pressure of the deep. They have completely forfeited the grace of the sky for ultimate resilience in the ice. Yet, within this perfect design, there's a profound, almost cruel irony. The exact same biological armor that protects the penguin from freezing to death creates a massive risk of overheating. When a penguin is exerting massive amount of energy, chasing down agile prey underwater, or awkwardly climbing up a steep, sunlit snowbank on a rare clear day, its internal furnace roars to life. The heavy blubber and the dense, vacuum-sealed feathers that keep the cold out also trap the excess heat in. The bird risks cooking itself from the inside. To prevent this, the penguin must actively vent its heat. It possesses a remarkable ability to temporarily bypass its own countercurrent heat exchange system. It forcefully flushes hot arterial blood directly into the vessels of its skin, its face, and its flippers. It holds its rigid wings far out from its body, exposing the lightly feathered undersides to the freezing air, acting like biological radiators bleeding excess warmth into the wind. In extreme cases, they will open their beaks and pant, using the evaporation of moisture from their lungs to dump heat, exactly like a dog on a hot summer day. The battle, therefore, is never simply against freezing. It is a constant, unending war against thermal imbalance in either direction. When the penguin returns to the ocean to feed, the demands of the cold merge terrifyingly with the demands of the deep. As it plunges hundreds of feet down, hunting for krill and silverfish, the hydrostatic pressure increases exponentially. The precious layer of insulating air trapped in its feathers is crushed to a fraction of its volume. The bird becomes heavier, sinking faster, but its insulation drastically diminishes. The deeper it goes, the colder the water feels against its skin. Simultaneously, the duration of the hunt is strictly bounded by oxygen. The penguin cannot breathe water. Its muscles are packed with incredibly high concentrations of myoglobin, an oxygen-binding protein that turns their flesh a dark, rich, almost black-red. This acts as a chemical storage tank for oxygen, allowing the muscles to fire long after the breath in the lungs has been exhausted. As the dive lengthens, the penguin's heart rate plummets from over 200 beats per minute at the surface down to single digits. Blood is aggressively shunted away from the stomach and extremities, prioritizing the brain and the heart. The body becomes a dark, silent, carefully rationed submarine, perfectly balancing the desperation of oxygen starvation with the encroaching, lethal grip of the cold. The cold ocean, initially perceived as nothing more than a hostile threat, reveals itself to be the master sculptor of the penguin's entire existence. It has dictated the microscopic structure of their feathers. It has woven the complex vascular nets inside their limbs. It has written the brutal metabolic rules of their starvation, and it has engineered the complex, fluid geometry of their social huddles. Every single physical adaptation, every behavioral instinct, serves one central, overriding purpose: maintaining a tiny, burning spark of internal constancy, while external forces attempt to ruthlessly strip it away. But this equilibrium, forged over millions of years of ice ages and evolutionary refinement, is incredibly fragile. The penguin is a master of the freezing world, but its mastery is locked within a very narrow, specific environmental window. As global climates shift, the parameters of their survival are being rewritten. Changes in sea ice extent determine how far they must walk to reach the ocean, burning precious calories before the hunt even begins. Warmer waters alter the delicate upwelling currents that feed the krill, pushing their prey further out into the vastness of the sea. Ironically, An environment that becomes even slightly warmer can catastrophically destabilize a biological machine built entirely for absolute zero. Too little ice, and the stable breeding platforms collapse beneath the colonies. Too much instability, and the precise timing of their fasting and feeding cycle shatters. As twilight settles over the endless, white expanse of the Antarctic horizon, a colony stands resolute against a pale, bruised sky. The wind begins to scream across the surface, lifting heavy crystals of ice into the air, transforming the landscape into a blinding white weapon. Within the massive huddle, thousands of bodies press close, feathers interlock with feathers, skulls tucked beneath wings, hearts beating quiet, rhythmic synchronization against the void. Miles away, far out at sea, another penguin suddenly breaks the surface of the black water. It exhales a sharp, misty burst of stale air, instantly inhales a freezing wind, and slips silently back beneath the fractured ice. The ocean continues to pull at every single molecule of warmth it can find. The wind continues its endless, screaming assault. The cold never, ever relents. And yet inside each compact, perfectly engineered form, life persists. It holds a line at a stable, unwavering internal temperature. Blood circulates through countercurrent networks, pulling heat from the brink of destruction. Fat fuels a steady, unyielding metabolism. Feathers trap invisible, life-saving shields of air. In the penguin, biology and behavior have merged into a single, flawless solution. Hold the center steady, guard the spark, and endure while the world freezes around you. In a landscape defined entirely by ice, isolation, and absolute indifference, survival is not loud. It is not found in a single, dramatic moment of violent conquest. It is the quiet, unending triumph of equilibrium, maintained second by second, breath by breath, against a force that never stops pulling the heat away. A humpback whale can slowly, agonizingly starve to death while swimming through an ocean that appears to be endlessly, vibrantly alive. It is a leviathan, a towering titan of muscle, blood, and bone moving with impossible grace through the blue immensity of the sea. It is one of the largest predators to have ever existed on the planet. Yet, for months at a time, this gigantic engine of life does not take in a single ounce of food. It sings. It violently competes for mates. It migrates across thousands upon thousands of kilometers of featureless ocean basins, burning through the biological energy of its own body like a massive furnace running, without a fuel line. Every single, sweeping stroke of its massive tail, every thunderous breach that shatters the surface, every breath it takes under the tropical sun is powered entirely by borrowed time and stored reserves. It is a living testament to the terrifying reality that in the ocean, sheer mass alone does not guarantee survival. In fact, mass demands a ransom that is almost impossible to pay. To understand the humpback, you must look to the polar extremes of the Earth. When summer finally breaks over the frigid waters of the Arctic and the Antarctic, the ocean explodes into a brief, violent window of hyperproductivity. The ice retreats. The freezing waters churn, drawing deep, ancient nutrients upward from the abyssal plains toward the light. Microscopic phytoplankton bloom in numbers so vast, they stain the ocean in swirling clouds of brilliant green, capturing the endless summer sunlight and converting it directly into chemical energy. In response, the zooplankton rise. Billions upon trillions of krill, tiny, shrimp-like crustaceans barely an inch long, swarm in concentrations so dense they form living, red rivers stretching for miles across the freezing sea. This is the great feast. And this brief, fleeting window of abundance is the sole, terrifying factor that determines whether a humpback whale will survive the coming year. The whale arrives at the feeding grounds entirely depleted. The long, grueling migration from the tropics has stripped its body of its fat. Its frame is lean and highly streamlined. The deep, parallel grooves running along its throat, the ventral pleats, are folded tight and flat against its underside. Beneath its thick skin lies a layer of blubber, but it is thin, dangerously exhausted from the exertion of travel and the heavy, parasitic toll of breeding. What follows over the next few months is not casual, leisurely foraging. It is a desperate, relentless military campaign of caloric accumulation. To harvest these microscopic prey, the humpback does not gently filter the water. It employs a hunting technique known as lunge feeding, a terrifying biomechanical feat that pushes the absolute physical limits of muscle coordination, hydrodynamics, and structural stress. When the whale locates a dense patch of krill, often detecting the swarm through subtle shifts in water density, microscopic visual cues, or the acoustic signatures of school, it dives deep below the prey. It aligns its massive body and accelerates upward. The whale surges toward the surface with blistering, explosive speed, its pectoral fins snapping out to stabilize its trajectory like the wings of a fighter jet. At the absolute last possible fraction of a second, the mechanics of the skull unlock. The massive lower jaws swing open to an impossible angle, approaching 90 degrees. Simultaneously, the elastic tissue of the ventral pleats suddenly unfurls. The throat balloons outward, expanding like a colossal underwater parachute. In the blink of an eye, the humpback engulfs a volume of water and prey that can mathematically exceed its own massive body weight. The mouth transforms from a streamlined jaw into a cavernous, dark abyss filled with violently swirling seawater and trapped krill. But this maneuver comes with a staggering, almost catastrophic physical penalty. The moment a whale opens its mouth at high speed, it introduces immense, violently opposing drag forces. The water resistance spikes exponentially. The whale's forward momentum is instantly, brutally arrested, like hitting an invisible brick wall. The colossal hydraulic load of thousands of gallons of water smashing into the open mouth transfers directly to the structural elements of the skull and the lower jaw. The bone and connective tissue must withstand this explosive pressure without snapping. Highly specialized sensory organs embedded deep along the jawline act as real-time stress monitors, coordinating the exact time of the lunge and ensuring the whale forcefully clamps its mouth shut just milliseconds before the structural limits of its own skeleton are catastrophically exceeded. Once the massive jaws finally slam shut, trapping the ocean inside, the second phase begins. The whale uses its massive, muscular tongue to slowly, forcefully push the water back out of its mouth. The water is forced through baleen plates, hundreds of thick, fibrous, keratin fringes hanging from the roof of the upper jaw, like a dense, bristly broom. These plates act as an impenetrable biological sieve, allowing the seawater to rush back out into the ocean, while trapping millions of squirming krill inside the mouth, ready to be swallowed in one massive, concentrated gulp. But here lies the absolute, terrifying razor's edge of the humpback's existence. Every single lunge costs a devastating amount of energy. Acceleration requires the violently powerful contraction of the massive axial musculature running along the entire length of the whale's spine. The tail fluke, broad, heavily muscled, and deeply notched, must drive a 40-ton body vertically through the heavy water. Because the lunge violently kills their momentum, humpbacks cannot swim continuously while feeding. They must constantly stop, swallow, reset, and accelerate all over again from a dead halt. The metabolic expenditure of a single lunge is astronomical. Therefore, the whale is playing a high-stakes game of biological poker with its own life. If it lunges into a patch of krill that is too sparse, the calories burned performing the physical maneuver will completely outweigh the calories gained from the swallowed prey. The whale will have effectively spent more energy eating than it received from the food. It is entirely possible to actively hunt to death. The efficiency of this brutal strategy depends entirely on the quality and density of the krill patch. Dense aggregations make the terrifying physics worthwhile. Sparse patches equal a net loss. To tip the odds in their favor, humpbacks have developed a layer of social coordination and hunting intelligence that borders on profound. In certain highly productive regions, these solitary giants abandon their independence and engage in a breathtaking cooperative hunting strategy known as bubble netting. A group of whales, sometimes numbering up to a dozen, will dive in perfect synchronization beneath a massive, frightened school of herring or krill, working together in the black water. They begin to swim upward in a tightening spiral, intentionally exhaling precisely measured bursts of air from their blowholes. The rising bubbles expand as they ascend, forming a thick, cylindrical curtain of air, a visual and acoustic wall that the panicked fish refuse to cross. The prey is effectively corralled, herded tightly into the center of the shrinking circle of bubbles. Down below, the whales orchestrate their strike using deep, low-frequency vocalizations, hunting calls that vibrate through the water column, synchronizing their movements in the dark. At the exact same moment, The entire pod surges vertically upward to the center of the bubble net, their massive mouths gaping open simultaneously, breaking the surface in a violent, chaotic explosion of churning water, escaping air, and fleeing fish. This behavior is not random. It is calculated, architectural predation. They are constructing temporary traps out of breath to maximize prey density and minimize escape routes. Cooperation drastically enhances the energy return per lunge, but also introduces intense competition. Each whale must maneuver its massive body flawlessly within the tight confines of the group to ensure it captures its fair share before the fish scatter. The goal of this frantic, exhausting summer feast is not merely daily sustenance. It is the construction of a biological savings account. A humpback's basal metabolic rate is massive, but because of its sheer volume, it is highly efficient. The calories from billions of krill are rapidly converted and packed onto the whale's frame as a thick, dense layer of blubber. As the long polar days begin to shorten and autumn creeps across the ocean, the prey abundance inevitably collapses. The krill vanish. The phytoplankton die off. The great banquet is abruptly over. And so, the humpback's body composition entirely changes. It is no longer a lean hunting machine. It is heavily insulated, carrying tons of energy reserves. Driven by ancient, inescapable instincts, the whales abandon the freezing, food-rich waters and turn their massive heads toward the equator. The great migration begins. For thousands of uninterrupted kilometers, the humpback travels through the blue void, completely leaving its food source behind. In the warm, crystal-clear tropical breeding grounds, the water is a biological desert. Prey density is so low that opening their mouths would be a total waste of energy. The whale is now living entirely on the clock of its own fat. Every beat of its heart, every song sung into the deep, every mile traveled is paid for by the blubber laid down months ago in the freezing dark. During this breeding season, the physical demands only escalate. Massive males engage in brutal, exhausting physical combat for the right to mate, smashing their 40-ton bodies into one another, bleeding off precious stored energy in displays of violent dominance. They sing impossibly complex, echoing songs that reverberate for miles, an acoustic exertion that drains their reserves. But the most staggering biological burden belongs to the mothers. A female humpback will gestate her massive calf, give birth in the warm, safe tropical waters, and then begin the unimaginably draining process of nursing. Humpback milk is incredibly rich, heavily concentrated with fat, designed to rapidly accelerate the growth of the calf, so it can survive the impending journey back to the ice. The mother is literally converting the melting blubber of her own starving body into milk to feed her child. She produces dozens of gallons of this rich liquid every single day, while she herself eats absolutely nothing. She will shrink. She will weaken. She will endure a state of extreme, self-cannibalizing starvation, perfectly balancing her own desperate survival with the absolute biological mandate to grow her offspring. The margin for error is effectively zero. This terrifying vulnerability reveals itself entirely when the delicate balance of the ocean's climate shifts. The humpback whale's massive, planetary life cycle is entirely chained to microscopic events. Climate variability dictates the extent of the sea ice. It dictates the strength of the deep ocean upwelling. It dictates the timing of the plankton blooms. If the water warms too quickly, or the currents shift, the krill do not swarm. A poor krill year echoes up the food chain with devastating consequences. If the prey density drops below the critical threshold, the whales cannot physically accumulate enough fat during the summer window. The consequences are not immediate, but they are an inescapable death sentence. A whale that leaves the polar waters without a thick enough layer of blubber will face a cascade of biological failures. Reduced fat means a weakened immune system. It means the mother cannot produce enough milk, condemning her calf to starvation. It means the whale may not have the cardiovascular endurance to physically survive the thousands of miles required to migrate back to the feeding grounds. Despite their incomprehensible size and power, humpbacks are finely tuned, hyper-delicate machines. Their survival is entirely predicated on a system of energy in versus energy out that cannot be cheated. To navigate this vast, shifting maze of energy, humpbacks rely on more than just instinct. They rely on memory and oceanographic intelligence. Beyond simple visual detection, they navigate along invisible thermal fronts, deep sea temperature gradients, and massive, swirling ocean eddies. These invisible oceanic features act as walls and funnels, concentrating microscopic plankton into predictable, dense feeding zones. The whale's migratory routes perfectly trace the geometry of these currents, suggesting a profound generational cognitive map of where the ocean blooms. But ancient memory cannot compensate for a rapidly collapsing system. In a changing world where historical feeding grounds turn barren, the whales are forced to travel further, searching desperately for new patches of life. Increased search time means increased energy expenditure. The brutal math of the lunge feed begins to fail. The margin between a biological surplus and a lethal deficit narrows until it disappears completely. Every anatomical system within this giant is tuned to this narrow, terrifying tightrope. Their skeletal structure is reinforced to survive the crushing impact of the lunge. Their massive circulatory system is built to flood dark red muscles with oxygen during repeated, exhausting dives. Their lungs are specifically designed to safely collapse under the immense hydrostatic pressure of the deep, forcefully driving air out of the delicate alveoli to prevent the absorption of nitrogen, effectively making them immune to the decompression sickness that would instantly kill a human diver. Every feature, every behavior, every cell is optimized to maximize feeding efficiency during a terrifyingly short seasonal window. As the brief polar summer finally draws to a close, a final, frantic urgency grips the feeding grounds. The whales lunge again and again, their jaws snapping shut on the dying blooms of krill, desperately packing the last few pounds of fat onto their frames. The ocean surface churns and violently ripples with the heavy, exhausted movement of the giants. And then, gradually they depart. The freezing waters grow quiet. The plankton fades into the dark. The colossal shadows turn south, vanishing into the endless, blue expanse of the pelagic void. Months later, thousands of miles away in a shallow, sun-drenched tropical lagoon, a massive mother and a rapidly growing calf break the surface together. The calf breathes deeply, its body surging with energy, its growth fueled entirely by the freezing, microscopic life its mother consumed half a world away. The mother exhales a slow, misty breath. She has not swallowed a single piece of food in months. With every breath she takes, her reserves shrink. With every drop of milk she gives, her own body dissolves. The ultimate limit of the humpback whale is not its staggering size, nor its crushing physical strength. The limit is the availability of microscopic, drifting animals in the most remote, hostile oceans on Earth. Their massive migrations, their haunting songs, their complex social bubble nets, all of it is completely dependent on a seasonal pulse of life driven by ancient currents, melting ice, and the angle of the sun. Remove or diminish that tiny microscopic pulse, and the greatest predator on the planet starves in the dark. In the brief, violent summer of the polar seas, the humpback launches upward once more. Its jaws open wide to engulf the ocean, playing a desperate game of physics and flesh against the clock. The sea may appear boundless and inexhaustible, but beneath the spectacle of the giant lies a cold, unforgiving ledger. Energy must always exceed energy out. And when the whale finally turns its massive head toward the equator, carrying the memory of the ice in its thick, heavy blubber, it proves that survival at the absolute extreme of scale is never about dominance. It is about timing, endurance, and the terrifying, beautiful fragility of a food web that stretches from an invisible cell of algae to the largest heart that has ever beaten in the sea. An octopus escapes through a hole no wider than its own eye, leaving behind a baffled predator that possesses the jaw strength to crush bone, but cannot follow its prey through solid stone. There is no dramatic, high-speed chase. There is no violent burst of acceleration, no desperate thrashing, and no bloody struggle in the water column. There is only a quiet, instantaneous vanishing act. One moment, the animal is trapped, cornered dead against a vertical reef wall, its skin flashing a dark, bruised red in a blare of biological alarm, its siphon pulsing rapidly as it processes the impending threat. The next moment, its entire body seemingly liquefies. It pours itself into a jagged, microscopic crack in the rock, its 8 arms folding, twisting, and compressing inward until absolutely nothing remains but a faint ripple of disturbed silt settling on the seafloor to mark where a complex, highly evolved animal once existed. In the crushing depths of the open sea and within the chaotic, high-traffic corridors of crowded tropical reefs alike, the ultimate prize of survival does not belong to the largest. It does not belong to the most heavily armored, nor the most violently aggressive. It belongs, unequivocally, to the most adaptable. The seafloor is not a gentle, forgiving landscape. It is a hostile, three-dimensional labyrinth of razor-sharp coral skeletons, violently shifting sands, jagged volcanic basalt, and vertical, dizzying drop-offs that vanish entirely into the blue-black emptiness of the abyss. Down here, hydrostatic pressure increases exponentially with every foot of depth. The light fades into a bruised twilight and invisible, tearing currents twist unpredictably around massive rock structures. In conditions as physically brutal, heavy armor becomes a massive metabolic anchor. Rigid, skeletal bodies become fatal liabilities when trapped. Predictable, linear movement is a death sentence. The octopus has evolved in direct, spectacular defiance of every one of those constraints. It carries no shell. Its skeleton is almost entirely absent, save for a microscopic internal remnant known as a gladius hidden away in some related deep-water species, and a single, hardened beak resembling that of a parrot buried deep at the center of its webbed arms. The entirety of its body is a fluid matrix of muscle, nerve, and skin bound loosely together by collagen and water. What looks to the uninitiated eye like profound physical fragility is, in fact, the ultimate evolutionary strategy. The defining, supreme advantage of the octopus is its absolute, unapologetic softness. Without a rigid cage of bones limiting its physical form, an octopus can radically compress its mantle and funnel its massive network of arms through gaps that defy the laws of geometry. The rule of its physical existence is simple. If its hard, keratinous beak, the single rigid structure in its entire anatomy, can pass through an opening, the rest of the body can follow. It does not simply squeeze, it pours. But this flexibility is not some random, flaccid collapse. It is highly coordinated, mathematically precise deformation. The arms of the octopus do not possess bones, but they are driven by a miraculous biological mechanism known as a hydrostatic skeleton. The arms are packed densely with alternating layers of circular and longitudinal muscle fibers. By rapidly altering the internal fluid pressure and shifting the tension between these opposing muscle groups, the octopus can instantly turn a soft, flowing arm into a rigid, impenetrable probing tool capable of prying open a clam, or a supple, prehensile ribbon that flawlessly wraps around jagged rock and struggling prey alike. In the most extreme environments of the ocean, this capacity for physical morphing becomes far more than just a brilliant escape artistry. It becomes the ultimate key to habitat access. The vast majority of oceanic predators, sharks, moray eels, large groupers, are trapped by the rigidity of their own skeletons. They are too large, too inflexible, or too wide to enter the narrowest, most deeply shadowed crevices of the reef or the volcanic rubble. The octopus, however, turns these cramped, claustrophobic spaces into impenetrable fortresses. It deliberately seeks out dens buried deep beneath heavy rocks, and then it goes to work. It does not merely hide, it fortifies. Using its incredibly dexterous arms, it collects heavy shells, discarded rocks, and ocean debris, methodically line the entrance to its den like a barricade. These are not accidental piles swept in by the tide. Observations in the wild show a deliberate, careful selection of materials and precise spatial placement. It is an act of engineering that violently suggests conscious planning and foresight rather than simple, blind, instinctive scattering. The den becomes a heavily fortified base of operations, a darkened vantage point from which the octopus can safely extend a single, sensory-packed arm out into the open water to scavenge, while keeping the vast, vulnerable majority of its soft body completely concealed behind a wall of its own making. Yet, physical flexibility and architectural defense alone cannot fully explain the sheer dominance and survival rate of this animal in low-visibility, high-threat waters. To understand the octopus, you must understand its mind. Intelligence fills the deadly gap where brute force fails. The brain of an octopus is not centralized in a single, protected skull in the same way that dictates the biology of vertebrates. While it possesses a central brain shaped like a donut wrapped around its esophagus, a massive portion of its nervous system, more than half of its 500 million neurons, reside entirely outside of its head. The mind of the octopus is distributed throughout its 8 arms, granting each limb an astonishing degree of semi-autonomous control. Each individual arm is lined with hundreds of highly sensitive suckers. These suckers do not just grab, they are packed with tens of thousands of chemical receptors. Every time the octopus touches a reef, it is simultaneously tasting it. Each arm can independently explore texture, map chemical gradients, and react to stimuli without ever needing direct oversight or permission from the central brain. In the murky, silt-choked depths where light scarcely penetrates and vision fails, this deeply distributed nervous system becomes a flawless, three-dimensional sensory net. The animal does not merely see the world it moves through. It feels it, tastes it, and calculates it continuously, processing millions of microscopic data points through a mind that extends to the very tips of its fingers. When vision is deployed, however, it is staggeringly powerful. The eyes of the octopus are an evolutionary marvel, highly sophisticated camera-like structures capable of detecting the polarization of light and registering the most microscopic shifts in contrast. Even in the dimmest, gloomiest conditions of the twilight zone, these advanced visual systems can easily identify the faint, rhythmic movement patterns that betray a hiding predator or perfectly camouflaged meal. But seeing the world is only half of the visual equation. The true magic lies in how the octopus forces the world to see it. The skin of the octopus is not a static barrier. It is a living, breathing canvas of deception. Embedded within the upper layers of its dermis are millions of specialized organs called chromatophores, tiny, elastic sacs filled with brilliant pigments of black, brown, orange, red, and yellow. Beneath these lie iridophores, which act as biological mirrors reflecting ambient light, and leucophores, which provide a stark white base layer to increase contrast. Every single one of these millions of pigment sacs is tethered to a complex network of radial muscles, which are wired directly into the animal's nervous system. When threatened or when hunting, the octopus does not simply hide behind a rock. It becomes the rock. In a fraction of a millisecond, the brain fires a signal. The radial muscles violently contract, pulling the pigment sacs wide open, flooding the skin with color. It can alter its pattern, its shade, and its brightness faster than a human can blink. But color is not enough to fool a sharp-eyed predator. The texture must match. The octopus forces specialized muscular nodes in its skin, called papillae, to instantly rise up, physically mimicking the jagged, abrasive roughness of coral or the smooth, undulating ripples of a sandy bottom. The deception is totally dynamic. As the octopus glides slowly over a reef, its skin continuously ripples and shifts, perfectly matching the changing background in real time. It is an active, ongoing, high-speed negotiation with its surroundings. The most baffling paradox of this system is that behavioral research strongly suggests octopuses are completely colorblind. They view the ocean in shades of polarized gray. Yet, they can perfectly match the vibrant reds of sponge or the deep greens of algae. They achieve this impossible feat by relying on intensely processed cues of brightness, contrast, and texture, using their skin as an automated translation of the environment. The brain interprets the visual input and translates it instantly into thousands of synchronized muscular signals. The result is an animal that can vanish completely, not by fleeing in panic, but by seamlessly blending into the architecture of the earth. Yet, even this godlike level of camouflage is not the pinnacle of the octopus's survival strategy. It is cognitive problem-solving that truly defines its reign in extreme conditions. In controlled laboratory settings, octopuses have repeatedly shattered the boundaries of what invertebrate intelligence was thought to be. They have been observed methodically unscrewing the threaded lids of glass jars from the inside to escape, or from the outside to access a trapped crab. They navigate complex, multi-stage mazes, retaining the spatial memory of the solution for months. They learn incredibly complex tasks simply by observing other octopuses perform them in neighboring tanks. In the wild, these staggering cognitive abilities manifest as sheer, opportunistic ingenuity. They have been recorded collecting discarded, hollowed-out coconut shells, stacking them together like bowls, and awkwardly carrying them across the exposed, dangerous mudflats. When a predator appears, the octopus instantly drops the shells, climbs inside, and pulls them shut like a biological armored personnel carrier. They find discarded glass bottles on the seafloor and use them as impenetrable, temporary refuges. This is not the blind, rigid, instinctive sheltering behavior seen in hermit crabs dragging borrowed shells. This involves conscious selection, awkward physical transport across long distances, and later mechanical assembly. It implies an understanding of the future. It implies foresight. In the crushing depth of the abyssal plain, where the pressure can shatter steel and the light from the sun has been dead for miles, species such as a Dumbo octopus drift like phantoms above the ooze. Down here, the absolute requirement for adaptability shifts radically away from camouflage and entirely toward brutal energy efficiency. Their movements are painfully slow, agonizingly deliberate. They conserve every microjoule of energy in a desolate environment where a single meal might be weeks away, and the oxygen levels hover near the lethal limit. The evolutionary absence of a heavy, calcified skeleton massively reduces the energetic cost of locomotion in the buoyant water. Their webbed arms ripple like heavy silk, generating just enough lift to glide without frantic, wasteful effort. Down here, intelligence manifests as perfect restraint, an absolute, unyielding refusal to waste resources. When it comes to the hunt, the flexibility of their strategy is terrifying. The octopus does not rely on a single, programmed method of attack. Some species will stalk heavily armored crustaceans by quietly extending a single, probing arm deep into a narrow burrow, relying entirely on the chemical-tasting sensors of their suckers to detect the faint, metallic trace of a crab in the dark. Others will ambush schooling fish by suddenly launching themselves off the reef, spreading the massive, parachute-like web between their arms, and engulfing the entire school in one sudden, inescapable motion. The choice of tactic is never uniform. It is a calculated decision based on a specific type of prey, the structural layout of the surrounding environment, and a highly advanced real-time risk assessment. An octopus confronted with venomous lionfish, armed with neurotoxic spines, would deploy a radically different, far more cautious approach than when encountering a harmless crab. If the hunt goes wrong, or if the hunter becomes a hunted, the octopus possesses an arsenal of deception. It may violently contract its mantle, forcing water out of its siphon to jet away at blinding speeds, simultaneously releasing a massive, billowing cloud of jet black ink. But this ink is not merely a visual smokescreen designed to hide a retreat. It is highly weaponized. The ink contains tyrosinase, a chemical compound that aggressively attacks and temporarily paralyzes the olfactory senses of a pursuing predator, essentially blinding the attacker's ability to track by scent. Furthermore, the octopus can mix the ink with mucus to form a pseudomorph, a dense, physical blob of ink perfectly shaped to match the size and profile of the octopus itself. Suspended in the water column, this phantom decoy distracts the attacker's bite for the crucial fraction of a second the octopus needs to vanish. Once again, survival hinges not on overpowering the threat with brute force, but on fundamentally manipulating the predator's perception of reality. But the ultimate tragedy of this magnificent, sprawling intelligence is the way it ends. Reproduction introduces a stark biological cruelty. The vast majority of octopus species are completely simmelporous. They reproduce exactly once, and then they are programmed to die. When a female octopus lays her thousands of teardrop-shaped eggs, she permanently seals herself inside her fortified den. For weeks, or sometimes many months, she will never leave. She will never hunt. She will never eat again. She dedicates the entirety of her remaining existence to guarding the strands of eggs, meticulously cleaning them with the delicate tips of her arms, and continuously using her siphon to blow gentle, oxygen-rich currents of water over them to prevent fungal rot. During this agonizing period of starvation, her body literally begins to consume itself. Her digestive gland breaks down. Her muscles atrophy. She loses her brilliant color, fading to a ghostly, sickly white. The optic glands in her brain secrete hormones that intentionally accelerate her own cellular death. Yet, through this entire horrific process of self-destruction, her cognitive capacity remains fiercely, stubbornly active. The exact same vast, distributed intelligence that was used to solve environmental puzzles on screw jars and outwit apex predators is now violently focused on maintaining the life of the next generation. She will fight off scavengers with her dying breaths until the exact moment the eggs begin to hatch. As thousands of microscopic, perfect replicas of herself drift up into the water column, she expires, her body dissolving back into the ecosystem she mastered. When those tiny hatchlings emerge, they are completely alone. There is no parental guidance. They are thrust immediately into a world that demands instant, flawless adaptability. In the shallow, sun-drenched reefs, predators are innumerable, and the competition for space is a brutal daily war. In the freezing deep sea, scarcity and crushing darkness dictate every waking second. In both of these extreme realms, the octopus survives only by exploiting the narrow, impossible margins that others cannot even perceive. The razor-thin spaces between rocks, the temporary architecture of discarded shells, and the momentary, engineered confusion of its enemies. Physical strength is entirely irrelevant when the body can simply reshape itself to avoid the confrontation entirely. There is a deeper, profound evolutionary twist embedded in this soft design. The complete absence of a rigid skeleton perpetually exposes the octopus to catastrophic injury. But this same vulnerability grants it an almost supernatural regenerative capacity. Arms lost to the jagged bite of an eel or the sharp beak of a dolphin do not spell the end. They simply regrow over time, complete with fully functioning neural networks and chemical sensors. Their intense neuroplasticity allows for continuous behavioral adaptation across their short, brilliant lifetimes. The very physical features that seem to invite the highest risk are perfectly offset by miraculous recovery mechanisms and an unending capacity to learn. The ocean does not reward rigidity. The sea is a force of constant, violent change. It shifts, it erodes solid rock, it obscures light, its pressure compresses, and its darkness conceals. In an environment defined by this level of chaotic flux, predictability is fatal. Holding your ground is a death sentence. The octopus answers the chaos of the ocean with absolute fluidity. It substitutes muscle and water for heavy bone. It substitutes towering, distributed intelligence for thick armor. And it substitutes infinite flexibility for territorial dominance. On a deeply shadowed reef face, as the light fades into the indigo of night, an octopus emerges cautiously from its den. The water is thick with microscopic plankton, the light dim, fractured, and chaotic. It extends a single, rippling arm out into the open water, tasting the invisible currents, sampling the chemical cues of the dark. A passing fish pauses, utterly unaware of the microscopic, instantaneous shift in pigment and texture that makes the massive predator hovering inches away completely indistinguishable from the encrusted stone. In a blinding flash, the hydrostatic muscles fire. The arms extend, the webbing unfurls like a terrible umbrella, and the prey is completely enveloped. It is subdued quietly with a paralyzing venom delivered through a hidden beak. Then the octopus slowly, fluidly retracts, retreating once more into the impenetrable darkness, sealing itself seamlessly within its chosen crevice. What remains visible to the ocean is not a monument to brute conquest. There is no shattered coral, no blood in the water. There is only quiet, flawless calculation. In extreme conditions of the earth, where strength and speed are brutally limited by pressure and starvation, intelligence becomes the ultimate survival trait. The octopus embodies an entirely different dimension of power, one rooted deeply in adaptation rather than force. Its survival is never just a single trick. It is an interlocking masterpiece of design, a liquid body, a decentralized mind, dynamic biological camouflage, chemical weaponry, regenerative tissue, and unparalleled behavioral flexibility. Each trait covers a weakness of the other, forming a system capable of surviving any uncertainty. Where other animals violently resist the environment, the octopus simply conforms to it, reshaping its physical form and its mental state exactly as the conditions demand. On the cold ocean floor, beneath crushing layers of shadow and pressure, a shape dissolves seamlessly into the rock once more. There is absolutely no monument to its presence. There is no evidence of a struggle. There is only a subtle, impossible shift in texture, where living muscle has simply become stone. In the harshest, most unforgiving corners of the sea, survival is not about overpowering your adversity. It is about becoming something that adversity cannot even grasp. A translucent cube drifts just beneath the surface of the water, so perfectly clear that it is nearly invisible. It has no brain. It possesses no centralized command center, no complex cortex to process the world, and absolutely no skull to protect the fragile spark of thought. And yet, This floating piece of living glass is about to execute one of the most mathematically precise, flawlessly coordinated hunts in the entire ocean. In the shallow, sun-drenched tropical waters of the coast, where the massive, twisting roots of mangrove trees plunge into the sea and tangle together like the skeletal fingers of drowned giants, the sunlight fractures. It breaks through the canopy above, piercing the water in shifting, shimmering columns of gold and green. Through this complex, densely structured labyrinth, a box jellyfish hovers. It does not simply drift. That is the first fatal misconception. The vast majority of jellyfish are passive, oceanic drifters, gelatinous balloons entirely at the mercy of the wind, the tide, and the current, responding to the world with nothing more than blind chemical reflexes. But the box jellyfish belongs to an entirely different, highly specialized lineage. It is an active, purposeful swimmer. It deliberately adjusts its orientation in the water column. It aggressively maintains its position against the pull of mild currents. It actively steers to avoid collisions with hard surfaces. For an organism built entirely out of soft jelly and loose nerve nets, this level of spatial awareness and physical coordination is deeply unsettling. It appears mathematically impossible. The architecture of the creature is deceptively simple. Its bell, unlike the rounded domes of its passive cousins, is forged into a distinct geometric cube. From each of its four corners trail incredibly long, highly contractile tentacles, armed with tens of thousands of specialized, microscopic stinging cells. But what truly sets this animal apart from the rest of the gelatinous drifters is not its venom, it is its perception. Embedded along the lower rim of its transparent bell are distinct, highly specialized sensory structures known as ropalia. There are four of these sensory clusters, one suspended on each side of the animal. And within these tiny, bulbous structures lie eyes. The box jellyfish does not merely sense light and shadow. It looks at the world across its four ropalia. It possesses a battery of 24 distinct eyes. Some of these are simple pits, designed only to detect the shifting intensity of the sun, telling the animal whether it is day or night, up or down. But others are staggeringly complex. Within these tiny clusters lie actual lenses, corneas, and retinas backed by photoreceptive cells capable of focusing light, distinguishing sharp contrasts, and forming crude spatial images of the environment around them. But here's a profound biological paradox. The jellyfish is all the sophisticated visual hardware, but has absolutely no brain to process the images. There is no visual cortex. There is no central processor analyzing the data. Instead, the nervous system of the box jellyfish is deeply, beautifully decentralized. The processing of the world does not happen in a central hub. It happens locally, right at the very edge of the body. Each ropalium is wired directly into a specialized nerve ring that tightly encircles the base of the bell. When the eyes detect the dark, vertical silhouette of a mangrove root, that visual input feeds instantaneously into the local neural circuit, which immediately triggers a corresponding motor response in the swimming muscles. The perception and the action are flawlessly, tightly coupled. There is absolutely no deliberation. There is no abstract thought, no hesitation, no planning. It is a living biological algorithm. This decentralized control grants the animal an almost mechanical efficiency. As the jellyfish pulses forward, it relies on rhythmic, highly coordinated contractions of specialized muscle cells embedded deep within the gelatinous matrix of its bell. Each powerful pulse aggressively expels water out of the hollow cavity beneath it, generating sharp, forward thrust. Between pulses, the natural, elastic recoil of its jelly-like body snaps it back into its original shape. This method of locomotion is astonishingly energy efficient, allowing the jellyfish to achieve surprising, sudden bursts of speed without the massive metabolic exhaustion that plagues muscular fish. As the afternoon sun begins to dip low on the horizon, painting the shallow waters in shades of twilight, the box jellyfish begins its daily migration. During the harsh daylight, it often retreats into the deeper, darker channels, avoiding the abrasive exposure to UV radiation and the sharp eyes of visual predators. But as dusk settles, driven by the simple, programmed threshold of fading light registered in its eyes, it moves purposefully toward the shallows. It is seeking the thickest clusters of mangrove roots, because that is where the microscopic larvae, the tiny crustaceans, and the juvenile fish gather to hide for the night. As it approaches a dense wall of twisting roots, the jellyfish slows its pulsing rhythm. It maintains a highly specific, calculated distance from the wooden structures. Laboratory observations have proven that this creature does not bounce blindly off obstacles like a robotic vacuum. It actively orientates itself relative to vertical silhouettes, purposefully threading the needle through open gaps in the wood to avoid tearing its incredibly delicate tissues on the barnacle-encrusted bark. It navigates the maze with the smooth, eerie precision of a phantom. A school of tiny, juvenile fish darts nervously between the roots, their silver scales catching the fractured, fading light. The jellyfish detects the sudden shift in contrast. It adjusts its trajectory slightly, turning its cubic bell toward the disturbance. Behind it, almost invisible in the gloom, its tentacles trail through the water like incredibly fine, lethal threads of spun glass. In this hunt, there will be no chase. There will be no biting, no tearing, no muscular struggle. The venom of the box jellyfish becomes relevant only at the absolute final microsecond of the encounter. The transparent tentacles drift silently into the cluster of hovering fish. The moment the microscopic flesh of a fish brushes against the tentacle, a biological landmine is triggered. The surface of the tentacle is packed with millions of nematocysts. These cells are loaded under immense osmotic pressure, acting like biological springs cranked to the absolute breaking point. The trigger is both mechanical and chemical. The physical brush of the fish, combined with the specific chemical signature of its skin, causes a nematocyst capsule to violently burst open. In a fraction of a millisecond, one of the fastest biomechanical processes in the entire animal kingdom, the microscopic harpoon everts explosively, shattering the cellular wall and firing directly into the flesh of the prey. It injects a payload of venom that is staggeringly, terrifyingly complex. This is not a simple digestive enzyme. The toxins of the box jellyfish are heavily engineered to aggressively target both the cardiac and the neural system simultaneously. In a small fish, the effect is not gradual. It is instantaneous, total, and irreversible paralysis. The electrical signals in the prey's nervous system are violently scrambled. Its heart stops firing, its muscles lock, and all struggling ceases within the blink of an eye. In humans, accidental contact with these invisible threads can trigger excruciating, paralyzing pain, catastrophic cardiovascular collapse, and rapid death. But for the jellyfish, this venom is not an act of malice or aggression. It is the ultimate extension of its biological simplicity. Because it lacks a heavy skeleton, tearing jaws, and grinding teeth, it cannot afford to physically fight its food. A struggling fish could easily tear the fragile, gelatinous bell to shreds. And so, the jellyfish allows supreme, weaponized chemistry to do all the heavy lifting. The paralyzed fish hangs suspended in the water, hooked securely by thousands of microscopic, venomous threads. Slowly, with measured contractions, the tentacles pull the immobilized prey upward, drawing it toward the dark opening of the mouth located exactly at the center of the underbelly. The process of feeding is as stripped down and efficient as the rest of the animal. Once the prey is transferred to the oral arms, potent enzymatic digestion begins immediately. Even while the fish is still partially outside the body, the fish is liquefied and the rich, caloric nutrients are drawn directly into the gastrovascular cavity. Inside this creature, there is no pulsing heart to pump blood. There are no veins, no arteries, no complex circulatory system. It doesn't need them. The nutrients simply diffuse outward from the central cavity, moving slowly through the incredibly thin, watery tissues of the bell. Oxygen from surrounding seawater dissolves directly across the ultra-thin cellular membranes, covering its entire body. It is an organism completely stripped of internal bureaucracy. Its simplicity is the very source of its profound metabolic efficiency. Yet, even this perfectly optimized system is not immune to the dangers of the coast. Sea turtles, heavily armored and biologically immune to the devastating effects of the venom, actively hunt box jellyfish, crushing their delicate bells with heavy, keratinous beaks. Certain specialized reef fish will cautiously approach from above, carefully nipping at the edges of the bell while avoiding the trailing, lethal tentacles. And the environment itself is a constant, shifting threat. Fluctuations in salinity from heavy coastal rains or sudden spikes in temperature can drastically impact their survival rates. But as global oceans warm, the biological equation is shifting. The simple, highly efficient metabolism of the box jellyfish allows it to thrive in conditions that suffocate more complex, oxygen-demanding fish. Their populations are expanding, drifting into new territories, and fundamentally altering the local ecosystems they invade. Because they are such devastatingly effective predators of fish larvae and tiny crustaceans, a bloom of box jellyfish can drastically suppress the next generation of fish from ever reaching the reefs. They silently, ruthlessly regulate the population dynamics of the coast. This animal forces us to confront a deeply unsettling ecological truth. We are conditioned to believe that intelligence, complexity, and a highly centralized brain are the ultimate pinnacles of evolution. We assume that a creature without a mind must be helpless, passive, and entirely at the mercy of its environment. The box jellyfish shatters that assumption. It proves that supreme lethal functional sophistication can arise from the absolute barest neural architecture. Its completely decentralized nervous system is not a primitive failure. It is a flawless optimization for a very specific, highly demanding set of tasks. It only needs to know how to detect light, avoid a wall, and fire a harpoon. Everything else, memory, social bonds, strategy, fear, is biologically discarded as useless, metabolic deadweight. As the night deepens and the tropical moon casts a pale, silver glow of the mangrove shallows, the water becomes a theater of incredibly subtle, silent motion. The translucent cube continues its endless, rhythmic patrol. Its 24 eyes constantly process the faint, shifting contrast of the moonlight filtering through the roots. Its nerve rings hum with localized, electrical commands. Its bell contracts, expelling water, driving it forward through the dark. There is absolutely no thought behind the movement. There is no conscious intent driving the hunt. There is only the flawless, high-speed integration of sensory signal and deadly motor response. In the warm, crowded coastal waters where biological complexity often overwhelms and exhausts so many other species, the box jellyfish survives and dominates through a process of elegant, terrifying reduction. It is a creature with no brain, yet perfect perception. It possesses no strategy, yet executes with flawless success. It is a translucent, invisible hunter moving with silent, mechanical precision, proving to the darkness that evolution can build absolute, lethal competence from nothing more than water, venom, and the barest blueprint of life. The silver flash lasts less than a single beat of a heart. One moment, the edge of the coral drop-off is a picture of absolute, hypnotic calm. A loose, shimmering cloud of sardines hovers in the warm water, catching the refracted sunlight, casually feeding just above the safety of the coral heads. The next moment, the water simply detonates. The sea erupts in a glittering, violent shockwave of torn scales. The synchronized school shatters, body scattering in every conceivable direction in sheer, blind panic. And straight through the dead center of the swarm, something long, metallic, and impossibly fast slices the water like a biological scalpel. By the time the surviving fish finally register what has just happened, one of their own is already gone, erased from the water column. This is the domain of the barracuda. It does not stalk the shadows like a moray eel. It does not rely on the patient, camouflaged infiltration of a stonefish. It survives on one singular, overwhelming advantage: explosive, ballistic acceleration so utterly extreme that the concept of reaction time itself becomes completely irrelevant. In the open, highly exposed margins of the ocean, the dangerous twilight zones between the labyrinth of the reef and the vast emptiness of the blue water, prey animals can see danger coming from every direction. There is nowhere to hide. Down here, survival does not depend on the element of surprise. It depends entirely on a speed that simply defies anticipation. Watch a mature barracuda before the strike, and you will see a masterclass in suspended animation. It hangs almost perfectly motionless in the middle of the water column, a 5-foot-long spear of rigid muscle. Its pectoral fins make only the most microscopic, imperceptible corrections to hold its place against the current. Its coloration is a flawless, optical illusion designed specifically for the open water. It utilizes counter shading, a dark, bruised dorsal ridge that fades seamlessly into a pale, silvery underside. To a predator looking down from above, the barracuda's dark back vanishes into blackness of the deep ocean. To prey looking up from below, its pale belly dissolves perfectly into the bright, sunlit surface. Its flanks act like shattered mirrors, reflecting the fragmented light and the ambient blue, essentially erasing its physical outline. From a distance, it looks like nothing more than a trick of the light, a streak of fast-moving current. But beneath that sleek, ghost-like exterior lies a piece of biological machinery built exclusively for violent, instantaneous release. The Barracuda's body is an unadulterated hydrodynamic missile. However, its musculature is engineered on a fundamentally different philosophy than the endless cruising engine of the tuna. The tuna is built for marathon, relying on dark, red muscle fibers steeped in oxygen for sustained, unending motion. The Barracuda is built for the absolute sprint. Its flanks are densely packed with white, fast-twitch muscle fibers. These highly specialized fibers do not rely on a slow, steady burn of oxygen. Instead, they are designed to violently, anaerobically contract, generating a terrifying, massive burst of absolute force. The trade-off, however, is that they fatigue with punishing speed. This predator does not engage in long, exhausting chases. It does not run its prey down over miles of open ocean. It simply annihilates the physical space between itself and its target in a fraction of a second. Imagine a school of reef fish drifting along the edge of the abyss. They are not defenseless. They operate as a highly synchronized collective sensory network. Hundreds of wide, unblinking eyes constantly scan the blue for the slightest hint of an approaching shadow. Thousands of microscopic lateral lines trace the flanks of the fish, specifically tuned to detect the faintest, unnatural vibrations in the water. Their entire evolutionary existence relies on detecting a threat within milliseconds and firing an escape reflex. But the Barracuda does not announce its arrival. It does not gradually speed up. When it decides to strike, it does not slowly transition from zero to maximum velocity. It primes itself like a loaded gun. The long body arches just slightly. The deeply forked caudal fin, the massive tail built entirely for maximum thrust, stiffens into a rigid paddle. In the predator's brain, a cascade of neural signals floods the motor neurons with brutal electric efficiency. In less time than it takes a prey fish to complete a single panic sweep of its tail, the Barracuda launches. The water physically shears along its narrow, pointed snout. The predator holds its long body completely rigid, eliminating almost all hydrodynamic drag, channeling every single ounce of the tail's explosive force directly backward. The battlefield here is not space. The battlefield is the nervous system of the prey. Most small reef fish have a staggering reaction time, but the Barracuda compresses a mathematical interval between visual detection and physical impact so violently that the prey's escape algorithms simply fail to compute. By the exact moment the first sardine's brain registers the looming silver shadow, the Barracuda is already inside the perimeter of the school. The mechanics of the impact are surgical. As it closes the final inches, the Barracuda opens its jaws just enough, unlike a shark or a grouper, which use massive, crushing bite forces to hold and wrestle their prey. The Barracuda's mouth is lined with long, terrifyingly sharp, dagger-like teeth. They are not built for gripping. They are built exclusively for slicing. The Barracuda does not stop the fight. It delivers a devastating, sideways snap of its head, its teeth shearing flawlessly through muscle tissue and bone. It often cuts its target cleanly in half in a single motion, and the predator does not stop. Its massive forward momentum carries it completely through the frantic, exploding school and out the other side into the open water. Only then does it execute a sharp turn to survey the damage. But this breathtaking display of violence exposes the Barracuda's greatest biological limitation. Fast-twitch muscle fibers are highly explosive, but they burn through stored cellular energy at a catastrophic rate. Because the burst is anaerobic, it instantly floods the muscle tissues with a toxic buildup of lactic acid. The Barracuda physically cannot sustain this top-tier velocity for more than a few fleeting seconds. After the initial, blistering sprint, its power output drops off a cliff. If the strike misses, or if the prey manages to dodge that first fatal pass, the predator is forced to make a critical decision. It must either secure the wounded prey immediately or completely abandon the attempt. It simply does not have the metabolic stamina for a second chase. This strict, unforgiving physiological constraint heavily dictates the animal's entire way of life. Because it cannot afford to waste energy running down erratic targets, the barracuda rarely engages in active pursuit. Instead, it transforms into an ambush tactician. It constantly patrols the high-traffic corridors of the ocean, the sharp edges of the reef, the deep tidal channels, and the sudden drop-offs where deep water meets the shallows. These are the oceanic highways. The predator quietly positions itself at these choke points, waiting for the prey to come to it, perfectly conserving its fast-twitch reserves between attacks. Yet, raw speed is entirely useless without flawless precision. When you're moving at ballistic speeds, your visual processing must remain incredibly stable, or you risk completely missing the target or violently colliding with a jagged reef. To counter this, the barracuda's eyes are large and specifically oriented far enough forward on its skull to grant it a crucial degree of binocular overlap. This provides pinpoint depth perception, a rare and vital trait for a fish, allowing it to mathematically calculate the exact trajectory of a fleeing target while closing the distance at highway speeds. Simultaneously, its inner ear and its own highly sensitive lateral line system provide critical stabilization and targeting data. The barracuda reads the microscopic vibrations transmitted through the water. It feels the frantic, rhythmic microcurrents created by the synchronized swimming of the schooling fish. It does not just blindly fire itself into the center of the mass. It calculates the collective motion of the swarm and aims for the highest probability of impact. And there's a darker, secondary brilliance to this explosive hunting style. When the barracuda detonates the center of a school, the sheer, blinding chaos it generates becomes a weapon in itself. The synchronized formation of the prey completely shatters. Fish scatter randomly, losing protective advantage of the group. In this momentary, frantic confusion, isolated, disoriented individuals become infinitely easier targets for a secondary, slower pass. Often, the barracuda doesn't even need to consume the first fish it wounds. The wave of panic it creates physically dismantles the defenses of the entire school. But the barracuda is a machine bound by the laws of physics and biology, and it is not invincible. Its entire survival model hangs precariously on peak muscle output and flawless reaction time. As the fish ages, the pristine efficiency of those fast-twitch muscle fibers inevitably begins to degrade. Minor injuries that affect the perfect hydrodynamic alignment of its spine or the raw thrust of its tail fin drastically reduce its burst acceleration. For a predator that relies entirely on outspeeding perception, even a microscopic fraction of a second decrease in its top speed can mean the brutal difference between a successful kill and starvation. The environment, too, plays a massive role in its lethality. Water temperature directly influences muscle performance. In warmer, tropical waters, the barracuda's muscle contraction speed peaks, making its strikes even more explosive. But warmer water also holds significantly less dissolved oxygen. After a violent lactic acid-inducing burst, the predator desperately needs to replenish its oxygen to clear the toxins from its muscles and reset its fast-twitch fibers. In warm water, this recovery takes longer. The barracuda must slow down, ventilate its gills heavily, and wait. In cooler waters, the burst might lose a fraction of its explosive edge, but the oxygen-rich environment allows the fish to recover and reload its biological weapon much faster. This strict adherence to efficiency also explains a fascinating shift in the animal's behavior over its lifespan. Juvenile barracuda, lacking the sheer mass and absolute top-end speed of the adults, often hunt together in loose, coordinated squadrons. They use their numbers to forcefully herd smaller prey against a physical barrier of the reef, using teamwork to amplify the confusion. But as they mature, as their muscles thicken and their burst speed reaches its absolute physiological peak, the barracuda abandons the pack. It becomes a purely solitary assassin. Evolution dictates that once the machine achieves maximum individual efficiency, cooperation becomes an unnecessary burden. The mere presence of this solitary predator completely fundamentally reshapes the behavior of the entire reef. Smaller fish instinctively recognize the silhouette. They maintain a state of hypervigilance in the zones where a barracuda is known to patrol. Schools tighten their formations. Stragglers hug the sharp, abrasive cover of the coral closer than usual. A single, motionless fish suspended in the blue water exerts a psychological pressure that ripples across the entire ecosystem. But the most chilling aspect of the barracuda is its absolute, unwavering restraint. It does not strike at every silver flash that crosses its vision. It calculates the metabolic cost of every single movement with cold, instinctual precision. If the density of a passing school is too low, the barracuda holds its position. If the tidal current is unfavorable and will push it off course during the strike, it simply drifts away to seek more advantageous ground. It knows that every single burst of speed must justify the massive energy it burns. Out in the open blue, the barracuda's long silhouette glints like a polished blade left suspended in the water. It appears utterly calm. It looks almost lazy, drifting aimlessly on the edge of the drop-off. But this profound stillness is an illusion. It is the absolute conservation of energy. Within its tightly wound muscle fibers, a massive reservoir of potential energy simply waits for the spark. The slightest trigger, a sudden, erratic flash of silver scales, a microscopic deviation in the rhythmic swimming of a target, will instantly ignite the sequence. The massive acceleration, the brutal, slicing impact, the silence that follows, and then the slow, heavy recovery. The ocean around it quickly returns to a state of apparent normalcy. In an ecosystem where the slightest hesitation guarantees starvation, and where a fraction of seconds delay means a prey escapes, the barracuda thrives on a razor-thin, bleeding edge of reaction time. Its strategy is brutally, beautifully simple, yet biologically extreme. Push the muscle fibers to their absolute physical breaking point. Compress the tiny window of prey awareness until it vanishes entirely. Execute the kill before the lactic acid sets in. Survival here has nothing to do with patience, and everything to do with overwhelming, inescapable physics. The limit is muscle output. The currency is time. And in that terrifying microscopic margin between detection and death, the barracuda is absolute. A fish lies in plain sight, and the entire ocean around it behaves as if it simply does not exist. A tiny, translucent shrimp casually picks at the grains of sand resting just fractions of an inch from what appears to be a jagged fissure in a rock, oblivious to the fact that it is grooming the mouth of a killer. Small, brightly colored reef fish dart past its heavily encrusted dorsal ridge, their lateral lines failing to detect any rhythm of breathing. Even a cautious, highly experienced predator, a reef shark or a massive grouper, glides directly overhead, casting its shadow over the uneven terrain without altering its course by a single degree. Then, in a span of time shorter than a human blink, the sandy bottom violently explodes. The rock seemingly tears open. The water inverts, and something vanishes entirely between jaws that never even appear to be there. The sand settles. The illusion reassembles itself. The most venomous fish in the ocean has just fed, and absolutely no one saw it move. The stonefish does not stalk its prey in the shadows. It does not engage in high-speed, exhausting chases across the open water. It survives through an act of total, unyielding physical erasure. It presses its heavy, misshapen body against the coral rubble in the shallow, high-traffic tropical waters, and it simply becomes a terrain. Its body is a flawless mimicry of erosion itself. Its warty, scaleless skin is mottled and muted, chaotic shades of brown, gray, and mottled green, perfectly echoing the abrasive textures of dead, encrusted reef. But it does not just rely on its natural pigmentation. It actively cultivates the environment upon its own flesh. The stonefish allows algae to permanently colonize its dorsal surface. It permits heavy sediment, sand, and microscopic debris to settle and accumulate along its flanks. Unlike other fish that constantly twitch and scrape to keep their scales clean of parasites and growth, the stonefish invites the burial. It embraces the rot. Over time, the biological line between the living animal and the dead environment completely dissolves. These shallow reefs are not tranquil, static gardens. They are chaotic, high-stress intersections of predator and prey, where the tidal currents constantly shift the temperature and salinity of the water, and where the blinding tropical sunlight pulses in broken, hypnotic patterns through the rippling surface. Exposure in this zone is constant. Unlike the moray eel that retreats deep into impenetrable caves, or the stingray that buries its entire body beneath the sand to hide, the stonefish often sits openly, fully exposed on the bare substrate. It does not rely on concealment through distance or physical barriers. It relies entirely on deception through mistaken identity. It does not hide behind the coral. It is the coral, The absolute secret to this deception lies in an almost supernatural discipline of stillness. In the underwater world, movement is the ultimate betrayer. Most fish must constantly ventilate their gills to extract oxygen, an act that requires continuous, visible movement of the operculum, the bony gill cover on the side of the head. To a predator's eye, the rhythmic pulsing of gills is a flashing neon sign of life. The stonefish, however, has reduced this biological necessity to the absolute bare minimum. Its gill openings are uniquely small, restricted, and strategically placed, allowing the animal to quietly draw in water and push it out with almost zero visible disturbance to its outward profile. When it breathes, it does so with a ghostly silence, producing no outward plume of water or pulse of muscle that would alert a passing victim. Even its eyes, which are positioned high on the top of its flattened skull, protrude only subtly, completely failing to betray the symmetrical, recognizable outline of a predator's face. But stillness alone, no matter how disciplined, would not suffice to guarantee survival in zones so heavily trafficked and exposed. The reef is full of sharp edges, abrasive currents, and predators that probe the rocks for hidden invertebrates. The stonefish survives this physical abuse through staggering physiological resilience. Its incredibly thick, scaleless skin forms a tough, leathery barrier against minor abrasions and the intrusion of parasites. Beneath that armored skin, its muscle mass is incredibly compact and dense, coiled like a compressed spring, enabling explosive, violent action even after weeks of total, uninterrupted inactivity. Yet, the true, terrifying insurance policy against the dangers of living in the open stands along the crest of its back. 13 stout, incredibly thick spines rise like jagged, broken rocks along its dorsal ridge. Each of these spines is directly connected to massive venom glands buried deep at their base. These spines are not passive needles. They are highly evolved, pressure-activated delivery systems. They act like biological landmines. When a predator steps on the stonefish or attempts to bite down on its back, the sheer physical pressure depresses the sheath surrounding each spine. This downward force acts like a plunger on a syringe, violently forcing the venom upward through deep grooves running along the sides of the spine, injecting the toxin directly deep into the attacker's tissue. The toxin itself is a devastating, highly complex cocktail of proteins designed to inflict maximum biological chaos. It aggressively disrupts cellular membranes, completely short-circuits neuromuscular transmission, and triggers a level of excruciating, paralyzing pain that borders on the unimaginable. It causes massive, immediate tissue necrosis at the injection site. For a predator, the cause of mistaken bite is not just a ruined meal. It is severe, agonizing injury and very often death. The reef contains many venomous species, but the stonefish's strategy is entirely unique in its reliance on invitation rather than warning. The brightly colored lionfish flares its vibrant, striped fins to actively advertise its toxic spines to the world. The banded sea crite uses striking contrast to warn predators to stay away. But the stonefish blends completely into the background, fully accepting the terrifying risk that something much larger might step on it or bite it unknowingly. This paradox reveals a much deeper, profound evolutionary strategy. By appearing exactly like a harmless, inert piece of substrate, the stonefish reduces its predatory encounters to almost zero. It does not want to use its venom. The venom is the absolute final line of defense, the catastrophic failsafe, not the primary deterrent. And this is because venom production is metabolically expensive. Synthesizing these complex, devastating toxins demands a massive amount of internal energy and biochemical resources. The stonefish, operating on an incredibly low, sluggish metabolism, simply cannot afford the constant regeneration of spent venom. Every single unnecessary discharge is a massive biological cost that it might not be able to repay. Therefore, absolute efficiency governs its entire existence. Its survival relies heavily on the fact that the reef has a memory. Predators learn very quickly. A juvenile shark or a massive grouper that makes a mistake of sampling a stonefish and survives the agonizing encounter rarely repeats the experiment. Scar tissue and searing neurological memory reinforce total avoidance. Over evolutionary time, these violent, traumatic interactions actively sculpt the behavioral landscape of the entire reef. Certain microhabitats and stretches of rubble become de facto safe zones for the stonefish, simply because experienced predators have learned to subconsciously bypass them. In this magnificent way, the venom does far more than just offend the individual fish. It actively shapes the geography of fear across the ecosystem. The relentless cycles of the tides introduce another profound layer of stress that the stonefish has mastered. In the extremely shallow reef flats, the water levels can drop dramatically during the low tide, leaving small, isolated pools cut off from the ocean. As the tropical sun beats down on these shallow puddles, the temperature rapidly spikes to levels that would boil the physiology of an ordinary fish. Oxygen concentrations fluctuate wildly, plummeting as photosynthesis from the surrounding algae slows down. When the tide recedes, the vast majority of reef fish panic and retreat to the deeper, cooler, oxygen-rich channels. The stonefish, however, often simply remains exactly where it is. Its staggering tolerance for exceptionally low dissolved oxygen, combined with an ability to withstand massive shifts in salinity and heat, allows it to persist in environments where almost every other animal is forced to vacate. This extreme endurance results in heavily reduced competition. Prey species that are desperately seeking a final, shrinking refuge in these isolated tidal pools may suddenly find themselves sharing a confined space with what appears to be a completely inert rock. The illusion of the stonefish extends far beyond simple coloration. Its skin is covered in bizarre, fleshy appendages that break up its physical outline, creating highly irregular, jagged contours that completely disrupt the brain's perception of symmetry. To a prey fish constantly scanning the water for predators, biological symmetry is the ultimate cue of danger. Eyes, paired fins, a streamlined body. These are the signatures of a killer. The stonefish vehemently denies that cue. It completely abandons form. It adopts extreme asymmetry, overwhelming roughness, and total visual unpredictability. Evolution has refined this mimicry to such a granular degree that across the globe, different species of stonefish perfectly match the specific geological reef substrates of their exact geographic range. There is a subtle, almost philosophical reversal embedded deep within the survival strategy. Most apex predators advertise their vitality through motion. They display breathtaking agility, explosive speed, with a relentless, terrifying endurance of pursuit. The stonefish survives by violently suppressing every single outward sign of life. It trades dynamism and grace for absolute, heavy invisibility. Its success rate in a hunt is astronomically high precisely because the brains of its prey are hardwired to filter out non-moving, asymmetrical objects as irrelevant background noise. In a densely packed, highly visual reef crowded with a million shifting shapes, the stonefish weaponizes stillness. It allows itself to be misclassified as safety. When the moment of strike finally arrives, the mechanics of the hunt reveal a terrifying, hidden precision. When a prey fish wanders within the critical, microscopic range of its mouth, the stonefish does not lunge forward. It does not give chase. Instead, it expands its massive buccal cavity, the interior of its mouth and throat, at a speed that challenges the limits of hydrodynamics. This sudden, violent expansion generates a massive vortex of negative pressure. The water instantly rushes inward to fill the void, carrying the helpless prey along with it. The jaws snap shut simultaneously, and the excess, displaced water is forcefully vented out through the gill openings. The entire, devastating event can occur in a fraction of a second. There is no chase. There is no desperate struggle in the open water. There is absolutely no extended, wasteful expenditure of precious energy. After feeding, the stonefish instantly resumes its role as terrain. Its mouth closes, the sand settles, and the rock returns. Digestion proceeds agonizingly slowly, perfectly matching its sluggish, low metabolic baseline. Because of this extreme efficiency, it can endure vastly extended periods without a single drop of food. Yet another adaptation perfectly suited to an environment where prey availability can be highly variable. Energy conservation is a foundational pillar that underpins every single aspect of its design. But environmental changes driven by a warming planet introduce a terrifying new uncertainty to this ancient strategy. Massive coral bleaching events are fundamentally altering the coloration and the texture of the reef substrate. Bright, vibrant corals are turning bone white before being smothered by dark turf algae. Sediment runoff from relentless coastal development modifies the composition of the seafloor. The stonefish's entire existence relies on a highly precise, heavily evolved visual mimicry, tying its fate inextricably to the physical integrity of the reef. If the background environment changes faster than the slow, grinding machinery of evolutionary adaptation can track, the perfect illusion may falter. A brown rock sitting on a completely bleached white reef is no longer invisible. Yet, this lineage of fish has persisted across millennia of violent environmental fluctuation. Its incredibly broad physiological tolerance for exposure, heat, and hypoxia, combined with its dual strategy of absolute invisibility and devastating venom defense, provides it with a deep reservoir of flexibility. Juveniles often occupy slightly different, more sheltered microhabitats than the massive adults, effectively dispersing the species' risk across different environmental gradients. This plasticity suggests a profound resilience, though it does not guarantee invulnerability. In the broader context of the reef system, the stonefish plays a quiet, almost invisible regulatory role. By preying heavily on small fishes and wandering crustaceans, it acts as a localized anchor on population dynamics. Its mere, silent presence fundamentally alters the spatial behavior of every prey species in the area, enforcing a constant state of vigilance and actively shaping how microhabitats are used. The predators that have learned to avoid the stonefish's territories are forced to concentrate their hunting efforts elsewhere, redistributing the predatory pressure evenly across the entire reef. An animal that spends 99% of its life barely moving at all exerts a massive gravitational influence that is completely disproportionate to its physical activity. As the harsh afternoon light finally begins to shift and long, dark shadows stretch out across the coral rubble, the stonefish remains totally unchanged in its posture. The tide begins to pull back, and a thin, fresh layer of shifting sand washes over its flank, accumulating in the crevices of its skin, further erasing its outline from the world. A passing surgeonfish hesitates for a fraction of a second, sensing something entirely unspoken in the water, before turning away and resuming its feeding among the algae on a different rock. Somewhere nearby, a human diver slowly scanning the reef might look directly at the ultimate predator and see nothing but a lump of dead stone until a single, incredibly subtle blink of an eye betrays its terrifying presence. The reef is a chaotic theater of constant, frantic motion. Yet survival here does not always belong to the swift, the strong, or the agile. Sometimes, the ocean rewards the patient, the deeply venomous, and the utterly indistinguishable. Motionless amidst the unending chaos, armored not with heavy plates of bone, but with agonizing toxin, the stonefish endures the blistering heat, the tidal exposure, and the relentless scrutiny of 1,000 hungry eyes by simply refusing to appear alive at all. In a violent world where drawing attention to yourself almost always guarantees your death, it thrives by becoming the background. And as the currents sweep over its rigid, encrusted back and the vibrant life of the reef flows endlessly around it, totally unaware of the danger beneath, the line between the predator and the landscape disappears once more. The first touch should kill it. A tiny, vibrantly colored juvenile fish drifts just a fraction of an inch too close to a dense, swaying forest of fleshy tentacles. For almost any other creature on the reef, this proximity is a fatal miscalculation. Each of those soft, undulating threads is armed with thousands of microscopic, highly pressurized harpoons, permanently primed to fire. A single, accidental brush against those filaments can violently paralyze a small fish in an instant. The tentacles would immediately close around the thrashing prey. Venom would flood the muscle tissue, and the agonizing process of digestion will begin before the victim even fully understood what had happened. Yet, this fish does not recoil. It does not dart away in a panic. It presses closer. It deliberately lets the lethal tentacles graze its flanks, sliding its body directly into the heart of the trap. And absolutely nothing happens. The sea anemone continues its patient, brainless ambush, its tentacles extended into the shifting current like a living, biological minefield. Nearby, schools of damselfish actively avoid the area. Butterfly fish hover at a cautious, deeply respectful distance. Even the apex predators of the reef, the massive groupers and patrolling reef sharks, give this innocent-looking clump of tentacles a wide berth. The anemone stinging cells and the nematocysts are devastating mechanical weapons. They do not rely on a central brain to fire. They are triggered by a combination of physical contact and chemical recognition. When they discharge, they do so at explosive ballistic speed, injecting a complex cocktail of neurotoxins that instantly disrupt nerve and muscle function. For the vast majority of reef dwellers, the anemone is completely untouchable, a fortress of pain. But deep within that lethal, stinging crown, flashes of bright orange and stark white flicker in and out of view. A clownfish weaves effortlessly through the forest, brushing constantly against venomous filaments that would incapacitate and devour almost anything else. It darts, it pivots, it hovers lazily, and when a larger shadow passes overhead, it simply retreats deeper into the toxic embrace of the tentacles. This is not a display of biological recklessness. It is an evolutionary masterpiece. It is a highly negotiated chemical truce. The clownfish survives by wearing a disguise so flawless, the anemone does not even realize a fish is there. The skin of the clownfish is coated in a specialized, unusually thick layer of mucus. For most fish, mucus is merely a basic biological lubricant, a simple barrier against parasites and aquatic pathogens. For the clownfish, it is a biochemical shield. Sea anemones lack eyes and complex brains. They rely entirely on molecular recognition to distinguish food from themselves. Their nematocysts are triggered not just by the physical pressure of a fish bumping into them, but by the specific chemical cues radiating from the surface of the victim's skin. The clownfish's mucus actively hacks this system. It masks or perfectly mimics the anemone's own chemical signature. When a juvenile clownfish first arrives in an anemone after spending its early life drifting in the open ocean, it does not just confidently swim into the tentacles. It performs a terrifying, delicate acclimation ritual. It approaches cautiously, making incredibly brief, tentative contact with the absolute tips of the tentacles, enduring minor, painful stings. It retreats, hovers, and then touches again. Slowly, over the course of hours or days, the fish either acquires elements of the anemone's own chemical makeup and integrates them into its slime coat, or it biologically suppresses the triggering signals within its own mucus. The result is a flawless molecular invisibility cloak. The anemone literally touches the fish, and its chemical receptors register it as just another one of its own tentacles. The biological tripwire is disabled. This relationship is universally heralded as a classic example of mutualism, but its absolute foundation is built on biochemical espionage. The clownfish gains the ultimate refuge. The reef surrounding this alliance is a perpetual battlefield. Small, brightly colored fish rarely enjoy secure, permanent shelter. The branching fingers of coral provide hiding spots, but predators can easily shatter the branches. Deep rock crevices offer cover, but moray eels can extract the occupants in the dark. The anemone, by contrast, is an impenetrable, heavily armed fortress. The clownfish has simply chosen to live inside the weapon. In return, the anemone reaps the benefits of a highly aggressive, hypervigilant security guard. The clownfish is fiercely territorial, actively chasing away specialized predators like butterfly fish and sea turtles that possess the immunity required to slowly graze on the anemone's tentacles. Furthermore, the fish meticulously grooms its host, removing dead tissue and ocean debris. Its biological waste product provide a constant, rich stream of nitrogen and ammonia, acting as high-grade fertilizer for the microscopic, symbiotic algae that live deep within the anemone's tissues, massively enhancing the host's photosynthetic energy output. The simple act of the fish constantly swimming in and out of the tentacles increases the localized water circulation, preventing the anemone from suffocating in stagnant water. But do not let the bright colors and the apparent safety of this biological partnership deceive you. Within the swaying tentacles, the social dynamics of clownfish are as brutal and ruthless as the ocean outside. They live in highly compressed, incredibly strict, claustrophobic dictatorships. A single anemone represents a very finite amount of physical real estate. It cannot support an endless number of residents. Therefore, the society is ruled by a single massive, overwhelmingly dominant female. She occupies the absolute center of the anemone, claiming the safest, most protected space. Beneath her in the hierarchy is a single, sexually mature breeding male who is significantly smaller, and beneath him, relegated to the absolute outer fringes of the tentacles where the danger of predation is highest, are a handful of even smaller, sexually immature, non-breeding subordinates. This hierarchy is violently enforced through constant, subtle physical aggression, posturing, and size-based dominance. The dominant female actively terrorizes the subordinates, chemically and psychologically suppressing their growth and their reproductive development. They are permitted to exist within the safety of the fortress, but they are not permitted to thrive. They must wait in a state of suspended biological animation. However, the clownfish possesses a staggering evolutionary trump card to ensure the continuation of its lineage within these isolated fortresses. If the dominant female is eaten by a predator or dies of old age, the colony does not collapse. Instead, the surviving breeding male undergoes a radical, irreversible biological transformation. Because clownfish are protandrous hermaphrodites, meaning they are all born with the capacity to be male, but carry dormant female reproductive organs. The sudden absence of the female's oppressive dominance triggers a massive hormonal cascade in the male. Over the course of a few weeks, he rapidly increases in size. His gonads completely restructure, and he effectively changes sex, becoming the new dominant female of the colony. Simultaneously, the largest, most aggressive of the stunted subordinates is finally freed from suppression. It rapidly matures into the new breeding male, stepping up to take the vacant position. This profound reproductive flexibility ensures absolute continuity. They never have to leave the safety of the tentacles to find a new mate. The monarchy simply rebuilds itself from within. Survival here is a deeply psychological game. It is not just about resisting venom. It is about flawlessly navigating the violent, oppressive hierarchy of your own family while surrounded by a perimeter of lethal poison. And beyond the tentacles, the reef is always waiting. Groupers, wrasses, and snappers constantly patrol perimeter, their eyes locked on the flashes of orange. A clownfish that strays even a few inches too far from protective radius of the anemone risks immediate, violent pursuit. When threatened, the clownfish does not flee across the open water. It violently retreats backward, slamming its body into the anemone, pressing itself deep against the stinging tentacles that part harmlessly around it. The pursuing predator abruptly hits the brakes. Even species that possess a mild immunity to the stings will not risk full, blinding entanglement in the heart of the anemone. This creates a highly strategic, incredibly tense dynamic when it comes to feeding. Clownfish cannot graze on the reef. They must venture outward, facing the open water, to meticulously pick microscopic zooplankton and small invertebrates that are carried past by the ocean current. They remain permanently tethered to the anemone by an invisible leash of fear, rarely exceeding a distance of a few feet. This severely restricted foraging range limits their access to food, but it mathematically maximizes their probability of survival. It is a constant, agonizing trade-off between nutritional abundance and sudden death. Yet, this ancient, heavily negotiated alliance is currently cracking under the immense pressure of a changing planet. The clownfish's entire evolutionary strategy is inextricably tied to the health of the anemone, and the anemone is inextricably tied to the temperature of the water. As the global oceans absorb massive amount of excess atmospheric heat, the tropical waters are reaching temperatures that completely short-circuit the biology of the reef. When the water gets too warm, the anemone undergoes a violent stress response known as bleaching. It physically expels the millions of colorful, microscopic algae living inside its tissues, the very algae that provide it with a vast majority of its daily caloric energy through photosynthesis. The anemone turns a sickly, ghostly white. Without the algae, the anemone begins to slowly, agonizingly starve. It shrinks. Its tentacles become stubby, weak, and far less robust. Its venom production drops. For the clownfish, a bleached anemone is a collapsing fortress. As the tentacles shrink, the fish is increasingly exposed to the sharp eyes of the predators circling the perimeter. If the anemone dies, the clownfish is suddenly left hovering in the open ocean, wearing a bright orange suit of armor that offers absolutely no protection against teeth. Chemical tolerance cannot save a fish when the weapon it hides inside simply ceases to exist. There is a secondary, invisible threat sweeping through the water column. The ocean is absorbing staggering amounts of carbon dioxide, fundamentally altering the pH of the seawater, making it increasingly acidic. Scientific evidence strongly suggests that this creeping acidification acts as a neurotoxin on the brains of larval clownfish. When the eggs hatch, The microscopic larvae drift out into the open, pelagic ocean for weeks before they must navigate back to the reef and locate a suitable host anemone. They find their way home in the dark using an incredibly acute sense of smell, tracking the faint, specific chemical plumes released by the anemones. But in highly acidic water, this sensory perception becomes scrambled. The juvenile fish become chemically blind. They cannot smell the predators, and they cannot smell the safety of the anemones. They wander the open ocean, lost, until they are consumed. The clownfish's survival strategy is a layered, breathtakingly complex masterpiece of biology. It begins with microscopic biochemical adaptation, extends through a rigid gender-bending social organization, and integrates flawlessly into broader, chaotic dynamics of the entire reef ecosystem. Its bright, iconic coloration, which is so often perceived as a cheerful advertisement, contrasts sharply with the lethal, venomous neutrality of its host. The orange and white bands do not warn predators away. They merely signal occupancy to other wandering clownfish, stating clearly, this fortress is taken. The deepest revelation of this animal is that toxicity here is never truly conquered. The clownfish does not possess a magic antibody that neutralizes the anemone's venom once injected. It avoids triggering the weapon entirely. Its entire existence depends absolutely on maintaining a flawless, unbroken chemical compatibility. A sudden disruption in the composition of its mucus, a stress-induced shift in its own internal physiology, or being forcibly separated and placed into a different species of anemone can render it instantly, fatally vulnerable. As dusk settles over the sprawling architecture of the reef, the predators of the day retreat, and the terrors of the night begin to emerge from the shadows. The water grows cold. The anemone contracts slightly, its long tentacles folding inward, closing ranks of the night. The clownfish presses itself deeper into the center, nestling its soft body against thousands of living, pressurized threads of lethal toxin. In a world where danger radiates from every conceivable direction, where armor shatters and speed fails, survival sometimes means making the unthinkable choice to inhabit the threat itself. The clownfish has chosen a home that would violently kill almost anything else on Earth. Its ultimate protection lies not in thick scales, massive jaws, or explosive acceleration, but in the quiet, invisible mastery of chemistry. A microscopic layer of slime separates a life of total security from instantaneous paralysis. As the currents shift and the dark ocean breathes, the anemone remains anchored, its venom eternally ready. And within its lethal grasp, the clownfish moves freely, a bright, unbroken pulse of life inside a toxic crown, proving that the ultimate defense is not fighting the enemy, but convincing the enemy you were never there at all. Our planet has spent billions of years burying its greatest secrets, but the story of survival is etched into every fossil, every stone, and every drop of the ocean. If you want to journey deeper into the ancient past and witness the brutal, beautiful history of our world, do not let this journey end here. Subscribe to Earth's documentary. Join us as we bring the true story of our planet back to life. Leave a like if you survived the journey, and we will see you in the next era.